Thank you, everyone. To commemorate this special occasion, we are pleased to announce the release of the conference abstract book, which compiles the research contribution of our participants. May I request our chief guests and other dignitaries to kindly unveil the abstract book. Thank you, esteemed dignitaries, for unveiling the abstract book. To formally begin today's program, I now invite Professor T.S. Gomti Devi to deliver the welcome address.
Good morning to all present here. Respected chief guest, Professor Sumitra Panjobam, Dean School of Mathematical and Physical Sciences. Guest of honors, Professor Umesh B. Wakamare, Jawaharlal Nehru Center for Advanced Scientific Research, JNCA SR, Bangalore. Professor Ais Basantakumar Sharma, Department of Physics, Manipur University. President Professor A. Dilip Kumar Singh, Head of Department, Department of Physics, Manipur Universities, faculties, invitees, delegates, participants, students, media persons, and ladies and gentlemen. I, Professor T.S. Gomti Devi, on behalf of the organizing committee, would like to express our greatest pleasure to welcome you all to the inaugural function of International Conference on Advanced Material for Sustainability and Innovation, Energy, Environment and Health, ACAMSI 2025 on 12th November 2025 at Manipur University Auditorium. I would like to extend our heartfelt gratitude to Professor Sumitra Panjobam, Dean School of Mathematical and Physical Sciences, for graciously accepting our invitation to be the chief guest of this inaugural function. Thank you, Madam, for your kind support and encouragement in organizing this conference. We are grateful to Professor Umesh B. Wakamare, Fellow of National Academy, Fellow of Academy of Science, Fellow of Academy of Engineering, MRSI medalist, for his kind consent to be the guest of honor of inaugural function and delivering keynote address of this international conference. Thank you very much, sir, for your valuable presence and contribution. We are also thankful to Professor Basantakumar Sharma, Professor, Department of Physics, Manipur University, for his kind consent to be the guest of honor of today's inaugural function. Thank you very much for your untiring support and help in organizing this conference. I also would like to extend our heartfelt gratitude to Professor A. Dilip Kumar Singh, President of today's inaugural function and Head of Department of Physics, Manipur University, for his unwavering support and invaluable help in organizing this conference since the very inception of the idea of Akamsi 2025. Today we are organizing International Conference on Advanced Materials for Sustainability and Innovation, Energy, Environment and Health from today to 12 November to 14 November at Manipur University. The objective of this conference is to create a platform for global knowledge exchange where researchers in various fields of material science, in health, energy, and environment share their knowledge, innovation, and invention with a broader audience, benefiting young researchers, especially from the northeastern region. We hope that the scientific program of the conference be attractive, productive, enjoying meeting all and making new friends and finding new collaborators for the research. Lastly, we extend our warm welcome to all the participants and especially honored by the presence of distinguished speakers, fellows of national academies and guests from India and abroad such as Japan, China, USA, Korea, Uzbekistan, Nepal, etc. We hope that the participants, especially the young researchers, will get more benefit from this 2 days international conference. Thank you everyone. Once again, I extend a hearty welcome to you all. Thank you.
Thank you, ma'am, for your warm words. Next, I invite Professor K. Nomita Devi to address briefly about the significance of this conference and its objective.
Respected dignitaries on the dais, Professor Sumitra Panjobam, Dean School of Mathematical and Physical Sciences, Professor Umesh B. Wakmare, President JNCSAR, Professor H. Basantakumar Sharma, Department of Physics, Manipur University, and Professor Angom Dilip Kumar Singh, Head Department of Physics, and Professor Gomti Devi, Department of Physics, convener of this conference, esteemed delegates, deans of various schools of Manipur University, heads of different departments of the university, officers, invitees, participants, and members of the media, a very good morning to all. And it gives me immense pleasure to briefly introduce our conference, the International Conference on Advanced Materials for Sustainability and Innovation, Energy, Environment and Health, ICOMC 2025, organized by the Department of Physics, Manipur University, during 12 to 14 November 2025. The idea of organizing this conference emerged from our strong belief that scientific advancement and sustainability must include every region and every section of the academic community. While our northeastern region is immensely rich in both talent and natural resources, it has remained relatively underrepresented in national and international research platforms. ICOMC 2025 is therefore a step towards bridging this gap by creating a vibrant and inclusive platform for researchers, women scientists, and students from remote and emerging institutions to interact, present, and collaborate with eminent experts from across India and abroad. The central theme of the conference, Advanced Materials for Sustainability and Innovation, reflects our collective commitment to addressing global challenges related to energy, environment, and health. Over the next 3 days, the conference will explore how innovative materials and sustainable technologies can drive progress towards a cleaner, greener, and healthier world. So the deliberations will cover a wide range of topics, including nanomaterials and nanocomposites, metal organic frameworks, photocatalysis and environmental remediation, energy conversion and storage, green hydrogen, plasmonics and spectroscopy, semiconductors, biomolecular and functional materials, computational material science and modeling, and also artificial intelligence in materials design. These are not just academic areas. They represent the building blocks of the future. One of the key motivations behind ICAMC 2025 has been to encourage and empower young minds. To promote wider student participation, the organizing committee has made special provisions for partial travel support, free accommodation, and awards for the best poster and oral presentations. We are truly inspired by the overwhelming response from students and young researchers across India. Their enthusiasm reflects how deeply science continues to inspire the next generations. And we are also very deeply grateful to our eminent researchers, professors, and invited speakers who have extended their wholehearted support to this initiative. And I acknowledge many of them have graciously agreed to bear their own travel expenses so that we could allocate more resources to support the students. Your generosity and encouragement truly embody the spirit of scientific collaboration, mentorship, and shared growth. Thank you, everyone. And ICAMC 2025 will feature plenary lectures, invited talks, oral and poster sessions, and interactive discussions, all designed to promote an exchange of ideas and inspire new research directions. We are confident that these 3 days will witness exciting interactions, thought-provoking discussions, and new collaborations that will continue long after the conference concludes. We are proud to host 200 delegates from 58 institutions across India and from 6 different countries, representing regions as far as Tamil Nadu in the south, Delhi in the north, Gujarat in the west, and our own northeastern states in the east. Such diversity brings strength and richness to the conference, truly making ICAMC 2025 a national and international confluence of ideas. To conclude, we sincerely hope that this conference will not only enrich scientific understanding, but also ignite curiosity, collaboration, and confidence among young researchers from this region and beyond. On behalf of the organizing committee, I thank all the delegates, speakers, sponsors, and collaborators for their valuable presence and support. With these brief words of introduction, I invite everyone to actively participate in the sessions and discussions that will follow. I invite all of you to the cultural program in the evening today and conference dinner that will be organized tomorrow at the Department of Physics, Manipur University. And I am confident that ICAMC 2025 will be an inspiring and memorable experience for all. Thank you, everyone.
Thank you, ma'am, for your insightful address. Now it is my privilege to invite our guest for today's inaugural function, Professor Sumitra Phanjobam, Dean, School of Mathematical and Physical Sciences, Manipur University.
A very good morning to everyone present. Professor Umesh V. Wagmare, President JNCASR, who is the guest of honor of the inaugural function of the International Conference on Advanced Materials for Sustainability and Innovation, Energy, Environment and Health, ICAMC 2025, organized by the Department of Physics from the 12th to the 14th of November 2025, who's Professor H. Basantakumar Sharma, the co-patron of the conference and guest of honor of today's inaugural function, Professor Angom Dilip Kumar Singh, Head Department of Physics and the President of today's function, distinguished invitees, Professor M. Premjit Singh, Registrar, Manipur University, Professor N. Rajmohan Singh, former Vice Chancellor, DM University, heads of department, deans of different schools, faculties from the different departments of the universities, distinguished speakers, participants, friends from the print and electronic media, everyone present, and my dear scholars and students. Well, a very warm welcome to all of you. As a member of the physics family of Manipur University and being in the group of material science, I am immensely pleased to be a part of today's function. At this point, I would like to say that the Honorable Vice Chancellor of Manipur University was to grace the function. However, due to an unavoidable official work that came up in the last minute, he could not be with us today. So, as the Dean of the school, I have the privilege of representing him on this occasion, and I'm deeply honored to address you on his behalf. It would indeed have been a great pleasure to have him here, as he has been a strong supporter of such events, organizing conferences, encouraging research activities, and advocating academic vibrancy in the campus. The very fact that material science group in the physics department, as well as in the different science departments, are able to carry out the basic fundamental characterization is because of his support, especially in maintaining and in supporting the functioning of two very sophisticated and very fundamental equipments, which are central facilities, the X-ray diffractometer and the scanning electron microscopy. So with his support and of course with the able and efficient maintenance by the operators and the faculty in charge, these equipments that were bought some 20 years back are still functioning and helping us with our research. So this impressive gathering of researchers and scholars coming together to exchange ideas and engage in thoughtful discussions is a fine reflection of this academic vibrancy. Talking of vibrancy, I would like to also mention that especially for those who have come from outside, the university is witnessing another kind of vibrancy also, the University Week. The Manipur University Students' Union is organizing the University Week, which showcases the talents of our students, in cultural activities, sports activities, etc. And you can see a lot of happening in the university. So it is a very nice time for you to be here. Well, I would like to say that this conference is a landmark event for our department, something that we all have been looking forward to. The last time that a national conference in the field of material science was organized by the department was in 2014, so many years back, and therefore this international event has truly been long overdue. Talking of researchers in the field of material science, I think the department has come a long way, some 10-15 years back, when we had no facilities. We did not even have a high temperature furnace for material synthesis, but now with national fundings brought by the department as well as individual projects by the faculty members, the department has the basic equipments for fundamental research, characterization, etc. However, there is always a lack of facilities, and our students heavily depend on other institutions outside of the state, like in SSPL, NPL, IITs, etc., in different parts of the country. And that has helped, but it takes long for them to accomplish their work. However, they are very hardworking, and still we depend on different institutes for our characterization for our researchers. Now we have come from basic characterization to application part of research, where we can predict or the potential of applications. But device fabrication is something that we still need to build up on. And now with the new faculty members that have entered the department, the field of research the dimension has expanded, and I think we are entering into the very recent researchers in the field of material science. And I think this conference will be very helpful in building up collaborations and for future networks. So I take this opportunity to congratulate the Department of Physics, the conveners, Professor K. Nomita Devi, who has given a very detailed account of the conference that is to come in the coming days. Professor T. Gomti Devi, they are the conveners. Then we have the co-convener, Dr. T.H. Ibomsa Singh, inspired DST faculty, a very dynamic and reliable faculty and the youngest in our department. All the members of the organizing committee, I would like to congratulate them for their dedication, for their meticulous planning, and for their enthusiasm in hosting this conference on such a grand scale. The organizing team has been working tirelessly for months, and I'm delighted to see their efforts coming to fruition with such an immense and overwhelming response and participation. My special appreciation for the dynamic team of our very efficient research scholars for their tireless efforts and dedication. They have taken care to give final touches not only to the technical and academic sessions, but also to give final touches to beautify the department in the best way, cleaning, even painting the trees, etc., to ensure that everything is perfectly in order. So congratulations and a big thank you to all of you. We are deeply grateful to our distinguished speakers who, despite their very busy schedule, have taken the time to be here with us today, and your presence adds immense value to the conference. A heartfelt welcome to all the participants, researchers, academicians, and professionals who have come from far and near. Your presence here makes the event truly meaningful and successful. So the chosen theme of the conference, Advanced Materials for Sustainability and Innovation, Energy, Environment, and Health. I think it is both timely and significant because as we face global challenges now, which is related to energy, environmental degradation, and human well-being, it is very heartening to know that advances in material science and innovation can offer sustainable solutions to these very big global challenges. So through creativity, through collaboration, and cutting-edge research, we can indeed move towards a more sustainable and innovative world. The coming 3 days will witness presentations from experts as well as from the students and participants on recent advances and emerging trends in the field. I am confident that the deliberations and interactions during the conference will spark new insights, will spark new ideas, and it will foster collaborations, avenues for future collaborations. So I encourage the young participants, especially, to actively engage in meaningful discussions with the experts, with your peers. You ask questions, you showcase your work, share your thoughts, and make the most of the 3 days. Attending conference is not just about presenting your work. It is about getting exposure, building your confidence, making friends, bonding, networking, which are very essential in this present day of digital world and AI, and building collaborations, and most importantly, having an enjoyable and enriching experience. So once again, I welcome and thank all the speakers and participants, especially those who have taken the trouble to travel miles to visit Manipur, situated in the remote corner of the country, in spite of all the apprehensions you may have had before coming. I hope you have a pleasant stay. I hope you enjoy your time here and hope that you take wonderful memories of our beautiful state. Finally, I wish the conference a grand success and hope it leaves a lasting impact on all of us. Thank you.
Thank you, ma'am, for your kind and inspiring words. Now, may I have the privilege of inviting our guest of honor for today's inaugural function, Professor Umesh B. Wakmare, President JNC AISR, to kindly share his thought about his conference with us.
Thank you. Good morning, all. Professor Sumitra Panjobam, Professor Sharma, Professor Dilip K. Singh, Professor Nomita Devi, and Professor Gomati Devi, and all the speakers, guests here, and student participants. It's absolutely my pleasure to greet you this morning. Manipur University is a university which has sent out alumni all across the country. And I have met many of them, very bright students, extremely hardworking, motivated, and now I understand how they are so physically fit, hardworking, and talented, and culturally oriented after coming to this campus here. In fact, after spending 10 years in the US, when I returned back to India, my first paper published was with a student from Manipur. And indeed, I'm very delighted to be at Manipur University here today. In fact, I feel I should have come here a lot earlier than today, and I'm very grateful to Professor Dilip Singh for his kind invitation and his colleagues. This conference, the International Conference on Advanced Materials for Sustainability and Innovation, with focus on energy, environment, and health, is a very timely event, as pointed out by Professor Sumitra. The problem of energy, environment, and health are interlinked. For example, and they are global problems. They don't come from one region or one group of people. For energy, we depend on many other countries, as you know, geopolitically today the situation. For environment, as you know, pollution in one region leads to effects in another region, neighboring or even distant regions. And health, we just came out of the COVID pandemic. All of you are aware how global extent it was, the influence of this pandemic. So these problems are current problems, big problems, involve scientific challenges to address these problems, and addressing such problems cannot be done locally because they are global problems. They require collaborations between different people, different regions, different disciplines within science and technology as well. And I'm indeed appreciative of the Department of Physics to have taken lead in hosting this conference at Manipur University in the next few days. As you will see, the program of this conference, it involves people from physics, chemistry, and biology background, and I'm pretty sure that it will be a very enchanting interaction involving exchange of ideas across disciplines. In fact, something which has been emphasized by national education policy, the interdisciplinarity in education. The second aspect of NEP which this conference supports in a very beautiful way is integrating research with education. You know, the many young students here are going to benefit from interactions and listening to many of the speakers who are working at the frontiers of these interdisciplinary areas of research. Lastly, the young students, I have one message for them, and also in general. See, not having resources is a concern in India. We have very few human resources, meaning if you compare with the rest of the world, number of funded researchers per million is 1/6 of what is there in the United States. If the human resources are less, indeed, even the capital, the infrastructural resources are also much less. And this is linked to the fact that our percentage of GDP that is spent on research and development is less than 0.7% in comparison to 2% of the United States, or even higher in South Korea or Israel. So for us, there is no option but to work together, because whatever funding we receive, we need to share with each other the resources, need to exchange ideas, work together to make a difference until we sort of grow in both size and the funding resources. So one message is, of course, you have to work together. Very important. Second is, don't be afraid of stepping out of your comfort zone, because the problems that you will face in energy, environment and health may not involve your basic primary expertise, but your ideas in your primary core expertise will be relevant to tackling these problems. So please be bold, courageous in asking big questions. Answering them will involve finding resources and working together for them. And from that angle, I do feel this conference is a very welcome event which has brought together people from different regions, different disciplines together, and the areas covered here cover physics, biology and chemistry as well, touching these three thematic problems. I will not take long time because I think we are sort of short of reaching the next session. So it's a pleasure to be here with you. I tell you that most infrastructural facilities, other research institutions in India are supposed to be accessible to everyone, and particularly the ones in the Northeast. So please do not hesitate to reach out to some of us when you want to have access to certain research facilities or working together. And from that angle also, I feel this conference is a good forum for me to extend absolute cooperation and support from my institute, JNCSR, to the researchers in Manipur as well as other parts of the northeastern India. With this, I wish you all a very enchanting, interactive conference in the next few days and look forward to seeing you all. Thank you.
Thank you, sir, for your kind and thoughtful words. Now I have the pleasure of inviting our next guest of honor, Professor H. Basantakumar Sharma, to address the gathering.
Respected dignitaries in the dais, Professor Sumitra Panjabam, Dean School of Mathematical and Physical Sciences, and the chief guest of today's function, Professor W.C. Wagmariji, President JNCR and plenary speaker of this, keynote speaker of this conference, Professor A. Dilip Kumar Singh, Head Department of Physics, Manipur University, Professor Gomti Devi, and Professor Nomita Devi, co-conveners of this conference. Of the dais, Professor Raj Mohan Singh, ex-Vice-Chancellor, DM University, Professor M. Premjit Singh, Registrar, Manipur University, Professor O. Ratnabala, Department of Mathematics, Professor Dorendrajit, Professor Nimai of Physics Department, Dr. N. Raghumani Singh of Bhabha Atomic Research Center, Professor Mukherjee, other invitees, invited speakers, and students. Good morning and warm greetings from my side. It is indeed a privilege and a joy to join at the International Conference on Advanced Materials for Sustainability and Innovation, organized by the Department of Physics, Manipur University, during 12 to 14 November 2025. This gathering is more than a meeting of minds. It is collective commitment to solutions that matters. At its heart, the ICA-MSI 2025 champions on powerful idea that advanced materials can be catalysts for energy efficiency, environmental restoration, and human health. This conference brings together leading researchers, early career scientists, and industry partners to share breakthroughs and build collaborations with lasting impact. Let me begin by acknowledging our dedicated conveners, Professor K. Nomita Devi and Professor T. Gomti, and our co-convener, Dr. T. H. Ibomsa Singh, the INSPIRE faculty of the Physics Department, and the entire organizing team whose commitments has made this conference possible. ICAMSI 2025 focuses on nanomaterials and nanocomposites, materials for energy storage and conversion, photocatalysts, electrocatalysts, and green hydrogen, functional and biomedical materials, spectroscopy and plasmonics, environmental remediation, computational and AI-guided materials design. Its theme speaks to one truth, that materials is the mission critical for sustainability. Across plenary, invited oral and poster sessions, 3 vibrant tracks define the program: advanced and functional materials, materials for energy and environment, spectroscopy, and smart design. Plenary insights include thermoelectric, sarcogenides, turning waste heat into power through clever bonding and design, rear art top nanomaterials engineered for light harvesting and biomedical applications, Raman and Assar's diagnostics achieving molecular level sensitivity in healthcare. Invited and oral presentations push the boundaries further. Supercapacitors with hybrid graphene, cobalt, nickel hydroxide electrodes showing greater than 600 farad per gram. Green hydrogen via trimetallic LDH electrocatalysts with with oxygen vacancies and high stability. Low-cost plasmonic sensors using HDBD gratings, innovation from simplicity. Green synthesized zinc oxide, ferrite, silver nanoparticles for environmental remediation. And we proudly note that our chief guest, Professor Sumitra Phanjobom, contributes to this very fields through research on rare earth substituted iron zinc magnetite nanoparticles, a perfect bridge between scientific excellence and academic hardship. The message running through every paper poster is clear. Material choices and interface defines the future from energy to health to climate. ICAMSI 2025 is not just about data. It is about direction toward greener processes, cleaner technologies, and inclusive innovation. We draw inspiration from the messages of our patron, our Honorable Vice Chancellor, and the patron, Dean SMPS, that science must serve the society. The chairperson's reflections remind us that from non-stick fan into solar cell, materials define modern life and will define our response to climate change. Our gratitude extends to all sponsoring agencies and industry partners, Northeastern Council, BRNS, DRDO, NRF, CSIR, State Bank of India, Sharma Borders, Kamlangba Instruments, and academia, whose support makes this academic journey possible. Dear students and young colleagues, your posters and presentations speak of curiosity and rigor. Continue to ask bold questions. Seek connections between theory, characterization and applications. So it has been widely saying that the experimental physics, material physics do not have much of depth in theoretical physics, but we need very good theoretical background so as to explain our scientific results. This conference is your launchpad. Take up with confidence. As you attend the talks, ask yourself, what is the core materials inside? Can it scale sustainability? Who can I collaborate with next? So collaboration is very, very important these days. Manipur, the soil of India, is not only the land of beauty, but also growing hub of scientific energy. When global expertise meets the local talent and the institutional vision, the impact resonates far beyond the campus. Let us celebrate this spirit of knowledge, collaboration, and innovation. May ICAMSI 2025 inspire many more such initiatives in the years ahead. Thank you all, and my best wishes for grand success of ICMASI 2025. Thank you very much.
Thank you, sir, for your insightful address. Now it is my privilege to invite our presidents for today's inaugural function, Professor Angom Dilip Kumar Singh, Head Department of Physics, Manipur University, to deliver his address.
A very good morning to one and all here, particularly the dignitaries on the dais. And in particular, I would like to thank Umesh for agreeing to give a plenary talk and sort of grace the inaugural function as a guest of honor. And I think, as Umesh has said, that the students here should not be afraid to reach out to the institutes which have better facilities. And he has offered that he would be most ready to help you all. I think that deserves a big applause. And I mention this because for those of us who are here in the department, who are here in the university, if you just bother to go and check the instrument facilities available at ZNC ASR, it will be like your dream. You just please go back and check the website of ZNC ASR from where Umesh has come, and check the kind of facilities that they have. And I believe that given that this conference has brought out the diversity of talks and contributions, I think many of those students who are here and from this region should go and look at the website and be inspired. Be inspired that one day you should visit such labs and even more, because your thoughts should not only be confined to this country, but to other countries in the world, to other universities, institutes across the world. And I believe that having participated in this conference, you will be inspired to chart out a path of your own in terms of your academic curiosities, scientific curiosities, and your journey to do better in terms of academics as well as contributing back to the society. Because having had this kind of an experience, I think you need to share it with your neighbors, with your friends, with the students that you interact, and bring back the kind of talent that you have as a contribution to the society around you. And in particular, we need that very much at this point of time and for our state. So with these very few words, as we are exactly on schedule, let me stop here and wish you all the best. Have a good time. Enjoy the cultural events that we have today evening. Explore around and there are very vibrant activities going around in the campus. Have a good time. All the best.
Thank you, sir, for your inspiring words. As we approach the conclusion of today's inaugural function, may I invite Dr. Thangzam Ibomsa Singh, co-convener of this conference, to deliver the vote of thanks.
A very good morning, everyone. Esteemed dignitaries on the dais, the chief guest of today's inaugural function, Professor Sumitra Phanjavam, Dean, School of Physical and Mathematical Sciences, Professor Umesh V. Wakmare, President Jawaharlal Nehru Center for Advanced Scientific Research, and the Professor is Basant Kumar Sharma, Department of Physics, and a guest of honor of today's inaugural function. Professor Angom Dilip Kumar Singh, the head of the Department of Physics, Manipur University, the president of today's function, and the conveners of this very conference, Professor K. Nomita Devi and Professor T.S. Gomti Devi, Department of Physics, Manipur University, respected plenary speakers, invited speakers, dedicated organizers, diligent researchers, their students, members of the media, and to our valued guests who are present here and those who are joining online from the other side of the screen. Once again, a very warm good morning to you all. On behalf of the Department of Physics, Manipur University, and the entire organizing committee, it is my profound honor and a privilege to extend a heartfelt vote of thanks as we formally draw the curtains on this immensely successful inaugural function of the International Conference on Advanced Materials for Sustainability and Innovation, Energy, Environment and Health, ICOMC 2025. There is a saying, a journey of 1,000 miles begins with a single step, and this remarkable 3-day journey was set in motion by the guidance and the support of our esteemed dignitaries. First and foremost, we express our deepest gratitude to our Honorable Vice Chancellor, Manipur University, Professor Lokendra Singh, for his tremendous support and guidance, though our Honorable Vice Chancellor was not able to present it in today's inaugural function due to his unavoidable official urgent works. His support has been with us from the very beginning of this very conference, and we really thank Sir for that. We are also indebted to Professor Sumitra Phanjavam, Dean, School of Physical and Mathematical Sciences, Manipur University, for being the chief guest of today's inaugural function. Madam, your encouragement and insight were instrumental in bringing this vision to life. We extend our sincere thanks to Professor Umesh V. Wakmare, President JNCASR, and the Professors Basant Kumar Sharma for being the guest of honor of today's inaugural function and for sharing their valuable words and encouragement. A special word of thanks to our President of today's inaugural function and the Head of the Department of Physics, Professor Angom Dilip Kumar Singh. Sir, your leadership and vision are the cornerstone of this department. This conference stands as a testament to your commitment to fostering a vibrant culture of research and international collaboration. And most importantly, the conveners of this very conference, Professor K. Nomita Devi and Professor T.S. Gomti Devi. Thank you, ma'am, so much for your tireless efforts and seamless coordination in making today's inaugural function a grand success and a conference an exciting one. The soul of any conference is its intellectual discourse, and we have been truly blessed to our distinguished plenary and invited speakers from prestigious institutions across India and abroad. Your presence has been the highlight of this very event. To all the oral and poster presenters, the young researchers, PhD scholars, students, thank you. Your innovative work is the very reason why we are all gathered here. A conference of this scale does not happen by chance. It is the result of months of miraculous planning and the tireless effort by a dedicated team of organizers. We thank all the members of the National Advisory Committee and the Local Advisory Committee for their valuable feedback and suggestion. It would be extremely ungrateful on my part if I did not acknowledge the phenomenal works of our organizing subcommittees. The travel and accommodation, the food and hospitality, the technical team, the finance and the program management. We thank all the faculty members, the research scholars, and the non-teaching staff of the Department of Physics for masterfully handling the budget, the program schedule, and the immense logistical position ensuring everything ran smoothly. Our sincere thanks also go to the university administration for their continuous encouragement and to all those who have contributed directly and indirectly to the successful organization of ICOMC 2025. Organizing such an event requires a significant amount of financial support, and we are truly grateful to the various organizations that have provided their generous funding. Special thanks to the Northeastern Council, the Board of Research in Nuclear Sciences, the Defense Research and Development Organization, Anushandan National Research Foundation, the Council of Scientific and Industrial Research, the State Bank of India, Sharma Bros, Kamlang Instrument and Academia, and the Manipur University for their generous funding and sponsorship. We also extend our gratitude to the media fraternity for your coverage of this event and for sharing the highlight and the breakthrough of this conference with the wider public. Finally, to every single person in this auditorium, thank you for your participation and your shared passion for advancing science for a sustainable future. We hope you make these 3 days engaging and truly memorable. Thank you once again for being a part of ICOMC 2025. Thank you.
Thank you, Chair. With this, we conclude the formal proceeding of our inaugural function, the International Conference on Advanced Materials for Sustainability and Innovation, Energy, Environment and Health, ICOMC 2025. And I extend my heartfelt gratitude to all the dignitaries, faculty members, students, media persons engaged for their presence and participation. And also, we warmly welcome all the delegates and participants to join the dinner and the cultural program as scheduled. For now, please take some time to enjoy the refreshment before we proceed to the next technical session. So, all the delegates are requested to take a group picture. All the delegates are requested to come up on the stage to take a group picture. Once again, I would like to request all the delegates to come up on the stage to take a group picture.
All the participants are requested to be on the stage for a group photo. All the invitees and participants are requested to be on the stage for a group photo, please.
Now we will start our first technical session.
Thank you everyone for the photo session. Next, we will start our first technical session. And this session will be chaired by Professor Sumitra Phanjobam, Deal School of Mathematical and Physical Sciences. And our first speaker, plenary speaker, is Professor Umesh B. Wakmare, President JNCASR. Next will be followed by our second plenary speaker, Dr. Raghumani Ningthauzam from BARC. So I request all the delegates and participants to be in the hall. We will start our technical session shortly. These volunteers are requested to arrange for the technical session. Thank you, everyone.
For chairing the first technical session, I request Professor Sumitra Phanjobam to come up onto the stage to chair this session.
In the plenary session, the first speaker that we have is Professor Umesh V. Wagmare, President, JNCASR Bangalore. We are very delighted and fortunate to be hearing his talk. So Professor Wagmare is a fellow of the 3 National Science Academies of the country. He has vast experiences and he is a recipient of prestigious awards. I will not name all of them. There are so many, innumerable of them, but 2 awards that he has been awarded are the prestigious Shanti Swarup Bhatnagar Prize in Physical Sciences, CSIR India, and also the Infosys Science Prize, Engineering and Computer Science. And his field of research is in theory, modeling, and simulations of condensed matter and materials. He will be speaking on the topic, Converting Waste Energy to Electricity, Thermoelectric Chalcogenides. So I request Professor Umesh to please deliver the lecture, and the duration is for half an hour. Please.
Thank you, Professor Sumitra. Good morning, all, once again. It's my pleasure to talk to you about. So the top portion is getting covered up. If it's possible to. Anyway, let me get started. Okay.
So you have this mic.
Yeah,
It will take around 6 minutes.
that's okay.
6 seconds.
Thank you. I think this is okay. I don't need this. I'll use this.
Oh.
Thank you. Yeah. Oh, that's much better. Thank you. Thank you. So it's a pleasure to be here with you to talk about some exciting work we have done recently. This area of work belongs to the theme of this conference, particularly to do with energy and also environment. Secondly, it also will give you a message that there is a lot of fundamental science that is needed in tackling these important, challenging problems. And the third message is most of the work I'm presenting here is computational work, and it can be done in Manipur with access to a reasonable computer, possibly computer with say 10 nodes or 8 nodes. Yeah? So such work is possible with fairly moderate infrastructural resources. The topic is converting heat into electricity, and that is based on some class of advanced materials called chalcogenides. They have thermoelectric properties. Work was done by my student, Koendrila, Prasad, postdoc, and Ragya. And such work benefits from working with experimental colleagues. I'm fortunate to work with Professor Kanishka Bishwas, who's the experimental expert in thermoelectrics, and also Professor C.N.R. Rao, who gives us a lot of interesting chemical insights into materials which are necessary to do interesting work. So, all of you know heat. Heat is everywhere. There are 3 examples I give here. One is a steel plant from Steel Authority of India Limited. And you will see a lot of heat is generated in such a steel plant. There is a car which many of you use every day, and you will see from the engine as well as from the other parts of the car, lot of heat is generated. And the third example is more modern source of heat called data center. Data centers are the ones which host computing resources, HPC resources. In fact, with the advent of AI ML, the amount of energy usage in data center is growing very rapidly. It doubled in the last 5 years. And at present, it's about 1.5% of the global energy. It's a huge amount of energy which is spent in data center. And such a data center has to be cooled. So it has air conditioning associated with it, as in addition to powering up the HPC resources themselves. So 60% of the energy is wasted in the form of heat. Can we do something about it? Because heat, of course, will give rise to other secondary problems to do with environmental heating as well as use of fossil fuels. So if you look at the global energy growth, I'm sorry some of these bars are not coming up here, but this is the data center, this is the growth in electricity requirement which is expected in the next few years. You will see that it is all in thousands of terawatt hours. That's a huge amount of energy. And what is expected is the heavy industry and electrical transport, these bars are up to here, will be still dominating the growth in energy demand, particularly in electricity in the years to come. So these plants generate huge amount of heat, and there is a need to be able to recycle the heat into some form of energy that one can use. And you can already see that there is interesting science problem, because heat is not something you can store easily. It's a thermodynamic concept. So the thermoelectric material basically has a property as shown here. You have a source of heat, at a high temperature, and cool side of the environment is over here. And if you have a thermoelectric material which has N and P type, the electrons here and holes here will be generated at a higher concentration in the hot region, and then they will diffuse away to give rise to electrical current. Yeah? So if you have a thermoelectric material, N and P, you can generate electrical current and power certain devices from a heat gradient. And the properties of a material which are relevant to such an application is, the first is Seebeck coefficient, which gives you electrical voltage generated by difference in temperature. Second is electrical current, which is given by electrical conductivity. And the last is thermal current, which is given by the thermal conductivity K, arising from the temperature difference. So these are the material properties which are important to be able to convert heat into electricity. A real technological device will not work with just one unit like this. They always have a series of units, see NP, NP, and they are connected by one to another in a sort of series manner, and that gives rise to a reasonable amount of electrical power. Okay? So this is the concept that we have in mind, that you want to develop an advanced material which can be sandwiched between a hot and cold region, and that should generate electricity for you. It will serve two purposes. It will get rid of the heat that is generated. You won't need too much of air conditioning. And in the return, you will also generate electricity which can be fed back into powering the device itself. Yeah? So it's a very appealing technology. And the interesting thing is, in principle, all materials exhibit thermoelectric effect. Seebeck coefficient is non-zero for any material, most of the time. And the reason is there is no symmetry restriction. Yeah? See, for example, if you want to have a ferromagnet, the material cannot have time reversal symmetry. If you want to have a ferroelectric material, material cannot have inversion symmetry. In that sense, there is no restriction. So many materials can be thermoelectric, but it's quite a challenge, as you will see in the next slide, to have a material that is, first of all, efficient in converting heat into electricity. Secondly, it can be synthesized at large scale. And the third is, it should be also economic to be able to finally give back enough useful energy at a low cost. So there is something called as thermoelectric figure of merit, and this is what is the measure for assessing if a material will be efficient converter of heat to electricity. So this ZT factor involves Seebeck coefficient squared times electrical conductivity in the numerator, and it's divided by thermal conductivity and times temperature to make it dimensionless. Now you will see, physically it is very sensible to understand this figure of merit, because suppose you have a heat source and there is a cold heat sink over here. If the thermal conductivity of this material is very high, well, all the heat will be transferred from hot to cold end. So you cannot have a material which has a high thermal conductivity, and that's why it comes in the denominator here. At the same time, the numerator is called power factor, voltage times conductivity, voltage squared, and that should be as high as possible because you want to have large electricity generation from the temperature gradient. Yeah, so I'm sorry, some colors are not showing up well in this, but I guess you can make out that these are the properties that you need. And you can also use it in the reverse manner. You can flow electric current through a thermoelectric device and make it cool, use it as a coolant device. For example, it can be used in precision refrigeration by using electrical current. Now, this refrigeration is also very attractive because it doesn't involve Unfortunately, it involves a very amazing, interesting scientific challenges, because if you see, these are simple expressions for Seebeck coefficient, and this is electrical conductivity. This is something you have seen it in elementary solid state physics books. Electrical conductivity will increase if you have more carrier concentration, and it will decrease if the effective mass of the electron is high. On the other hand, Seebeck coefficient will increase if the effective mass is large and decrease if the the charge carriers are less in concentration. And unfortunately, that means if you want to increase Seebeck coefficient, electrical conductivity comes down. And if you increase electrical conductivity, thermal conductivity can go up, which is in the denominator. So you can't have everything increasing at the same time. And that's the materials challenge. How to have a material? You will see as a function of carrier density, Seebeck coefficient comes down. So if you have a metal, you have a very low Seebeck coefficient, but a high electrical conductivity, but they are not favorable to efficiency. And Seebeck coefficient typically peaks, the thermal current in conductivity is flat. So the ZT factor is high only in a very small carrier concentration, and which is typically in the border between metal and a semiconductor. Yeah? So the bottom line is, to develop an advanced material which is a good, efficient thermoelectric converter of energy, it involves conflicting design parameters. It's a challenge. So why are we thinking about chalcogenides? The reason is, there was a very nice work done by Matthias Wuttig's group here, as shown in this paper. They looked at a variety of materials in a plane of what is called as electron transfer and electron share between the atoms. Yeah? So chemists would like to call this is like ionic bond, and this will be, if the more electrons are shared, it's a covalent bond. You will see this corner is ionically bonded crystals. This region is covalently bonded crystals, and here it's metal because there are very few electrons shared or transferred. Yeah? And resonant bonding is somewhere over here, like benzene or graphene type of bonding. What is interesting is this region, I'm sorry the colors are really weak in the screen. This region is where they called it metavalent bonding. These materials are all chalcogenides and have a ZT factor greater than 0.25. So most high ZT factor thermoelectric materials fall in between covalent semiconductors here and metallic materials over here in this region. Yeah? Okay, so this is the background why we are interested, and these are all chalcogenides. These metavalently bonded materials are all germanium telluride, lead telluride, tin telluride, or selenide, and so on and so forth. So what is the bonding mechanism? So first step we do is, as a physicist, we want to understand what are the properties of these materials which are so special. And in fact, Wuttig et al. Had defined this metavalent bonding. You will see this column is metavalent bonding, this is covalent, this is ionic, and this is metallic. If you look at electronic conductivity, it's very low in these materials, it's very high in metals, it's intermediate for chalcogenides like germanium telluride and lead telluride. Effective coordination number rule is satisfied in this, but not satisfied over here. Then more importantly, Mohr-Gruneisen parameter, which is the nonlinearity in lattice dynamics, is moderate in all of these compounds, and it's extremely high in these compounds. As a result, this gives rise to low thermal conductivity, and it also has high electrical conductivity. And indeed, it's being a semiconductor also has a large Seebeck coefficient. So that's why the chemical bonding, which are characterized by these properties, make it a very suitable material for thermoelectric applications. So these rock salt structure, the structure of these chalcogenides is simple rock salt, like sodium chloride structure, and they really are very unique in their bonding properties, which make them special, because a thermoelectric material is efficient if it is metallic in electrical conduction, it is semiconducting in thermal conduction, Seebeck coefficient, and it's like glass, insulating glass in thermal conduction. So this is why it's an interesting set of materials. Yeah? So what are the electronic mechanisms? Being physicists, we looked at it in a very innovative way. We said we will start with a metallic state, some hypothetical metallic state, and continuously evolve them into these metavalently bonded chalcogenides, and then see how they will go into covalent and ionic bonding structures. Okay? So in physics, we call this as adiabatic evolution. You start from one state, and slowly change some parameter in the Hamiltonian, it will go transform your ground state from one to another. And that's what we did. This is the lead telluride material which we are interested in, lead chalcogenide. It's in the rock salt structure. We replace each lead and tellurium atom by the same atom, either tin or you can call average of lead and tellurium. Right? This is possible in theory, by the way. And I told you all the work I present is theoretical work. So these are materials which are same as the rock salt structure, where cation and anion is replaced by same atom, tin or some hypothetical atom. So the beauty is this structure is as close in structure and number of electrons to the lead chalcogenide that we are interested in. Once you do that, you will find out that this parent structure, where we have replaced lead and tellurium with antimony, is metallic, and lead telluride is a semiconducting material if you look at electronic structure. But more interestingly, you will see the bands are exactly very similar in both the compounds. Yeah? There are very simple differences you can identify. The degeneracies are split here, and the gap opens up in the valence, between valence and conduction band. And that's why the lead telluride is a narrow band gap semiconductor, which is very intimately linked with a metallic state called antimony in simple cubic structure. Once you know this, we looked at antimony, the parent metallic structure. The fundamental property of a metal is its Fermi surface. So we look at Fermi surface and find that it's actually nested. Nested Fermi surface means pink packet of the Fermi surface can be transformed to blue packet of the Fermi surface by a simple wave vector R, gamma to R. R is pi by A 111. Yeah? So when this happens, what it means is electrons in this packet can be scattered into electrons in this packet without any effort with the same perturbing field given by the wave vector R. And when that happens, you will see the phonons are unstable. This is phonon dispersion of the parent metallic structure, and you will see it's highly unstable at R point. And this is the indicator that the structure is unstable in the cubic form. It will like to lower its symmetry and open up a gap, and that's what we showed earlier. Yeah? So this is the fundamental physics, that these chalcogenides are intimately linked with metallic parent structure like antimony. So the essence of the work that we did is shown here. You start from the parent metallic tin-tin structure. Since it has a nested Fermi surface, it's unstable. It has a chemical instability. If you replace tin by lead and telluride or germanium and telluride, you get a semiconductor state, which is lower in energy. It can also undergo structural instability to give you a rhombohedral structure, which is also gapped. Or if you replace both, if you involve both instabilities, you get a ferroelectric structure. Now, this is very fascinating because this is one of the simplest ferroelectric you will have, which has a spontaneous electric dipole moment in the ground state. And this is a result of the fact that it's closely related to a metallic state. Yeah? So you have metal insulator transition and ferroelectric transition. Both involve breaking symmetry of the parent structure. That's what has been shown. So we illustrated it using first principles calculations. In this case, we are using, we break the translational symmetry using chemical field, meaning you start with an SB and replace one SB atom with bismuth and another SB atom, you retain it as SB. You open up a band gap in the electronic structure. And that's a lower energy structure. Secondly, you can also off-center the two atoms, so you have double atom unit cell. Every alternating atom, these arrows are telling you off-centering of atoms. If they form dimers, then you open up a gap again. And the resulting structure, which has a rhombohedral symmetry, is stable if you look at the phonon dispersion of it. So this is to illustrate that the fundamental physics of these chalcogenides comes from the parent metallic state, which is unstable. And if you break the symmetry of the parent metallic state, you get low energy state. And that's why the low energy state, like germanium telluride, is called incipient ferroelectric or incipient metal. Because what it means is material is being on the verge of becoming metallic, or it's on the verge of becoming ferroelectric. And that's the speciality. In fact, in my definition of advanced material, a material is an advanced material when it can go from one state to another very easily in response to a perturbing field or external field. So what we demonstrated is basically you can start from metallic structure and break symmetry structurally or chemically, you get metavalently bonded state. And these are the chalcogenides that I'm talking about. And if you break the symmetry even more strongly, you will go to covalent bonded and ionic bonded structure. So this is the beauty of this particular work. In chemistry, we talk about bonding as interactions between atoms mediated by electrons. In physics, we talk about bonding as a symmetry breaking sort of phenomenon, starting from a high symmetry parent metallic state. Okay, so with this, we determined the phase diagram. And again, I apologize for colors not coming out so well. In this picture, this is the metallic state, 0, 0. It's like a Big Bang theory. And you have a high symmetry phase in this corner. If you break symmetry chemically, you will get these chalcogenides. And if you break the symmetry too much, you get ionic compounds like barium telluride. If you break symmetry structurally, meaning you displace every alternate atom with respect to each other, you get zinc blende structure with a coordination number of 4, whereas here coordination number is 6. And this is a covalent semiconductor. And on the way to breaking the symmetry, this is the narrow region where you get metavalent structures, and those are the group 4 chalcogenides. So what we show in this phase diagram is, this is a very interesting phase diagram, not accessible experimentally directly, but you can look at many compounds which fall in this region are going to be metavalently bonded chalcogenides, and they come in between metallic state and ionic and covalent states. And that's why they have properties of all 3 materials, and hence they are good thermoelectric, efficient thermoelectric materials. Yeah? So, of course, electronic mechanism is not clear. So what we did is basically we looked at what are known as one-year functions. Professor Sumitra, please caution me when I'm 5 minutes. Yeah, thank you. So these are called one-year functions of electrons. Unlike block functions, which are extended states, one-year functions are like molecular orbitals in a crystal. And what you will see is this is one-year function centered on tellurium atom with a p symmetry. But you will see very spectacular feature. It bonds with the next p orbital in a sigma manner, and then anti-bonding with the next p orbital. And you will see there are pi type of interactions as well, which are anti-bonding interactions. And the same is seen for the other 2 types of one-year function. So interesting is the bonding in this material is highly delocalized. And it's extending to further neighbors, unlike a chemical bond in covalent case, which involves 2 atoms, or maybe in the nearest 3 atoms, 4 atoms. In this case, it's along a chain which extends 5 atoms the distance, or 2 unit cells along the axis of the chain. And they involve alternating sigma and pi type interactions. And that makes them very special, because when you have one bond which is anti-bonding, next bond is bonding, the electron can very easily hop from one to another, like in the conjugated polymers. Yeah? So that type of bonding here exists in inorganic chalcogenides. And that's what makes them special. So the next question we asked is, can we make, by the way, this was a question which was posed by Professor C.N.R. Rao, and we as physicists came in and answered this question in a very sort of clever way. The next part is about, now we understand these chalcogenides as a consequence of instabilities in the metallic state. Can we engineer these instabilities to get high performance thermoelectrics? And this is application of that fundamental idea. And you will see that if you look at germanium telluride, let me first tell you what we mean by structural instability. This is phonon frequency as a function of wave vector. These are imaginary phonon frequencies which are below 0. And this means these phonons are unstable modes, which define lattice instabilities. And if you dope this germanium telluride with lead and bismuth and selenide, you engineer this instability. This was very localized instability for germanium telluride. Now you have these instabilities everywhere in the reciprocal space Brillouin zone, and that makes it very special. If that happens, in this case, the off-centering gave you only homogeneous displacements of atoms, polar displacements. Here you have a combination of homogeneous and inhomogeneous displacements. And you basically get what is called as inhomogeneous ferroelectric instability. Yeah? So this is what we call engineering structural instability. You had a homogeneous structural instability. You made it very rich and inhomogeneous instability. As a result of that, you will see these unstable modes give rise to local random polar structural distortions, and they scatter the acoustic phonons very strongly. For the students in the audience, let me remind you that thermal conduction in a material is dominated by phonons, and particularly acoustic phonons, what you know as sound waves. Copper or gold is not at all a good conductor of heat. It is 10 times less conducting for heat than diamond, which is an excellent insulator. And the reason for it is diamond is super hard. Sound waves in diamond move at the highest velocity, and that's why you get high thermal conductivity in diamond. In this case, we managed to basically introduce these unstable modes which scatter the acoustic phonon modes, and as a result you get low thermal conductivity by making sure that tau is very small and velocity of sound is also small. Yeah? So this is the way we engineer ferroelectric instability to get low thermal conductivity. So here is experimental curve now, measured by Kanishka Vishwasa's group. You will see that thermal conductivity of germanium telluride is pretty high, but if you substitute these elements, it drops significantly and it remains essentially flat. You get glassy thermal conductivity, and as a result, they could achieve a ZT factor of almost 2.9 in this set of materials. This is a world record, okay? This is not a small achievement. This was published just this year in Advanced Materials, where theory and experiment came together to explain and design this material which has very high ZT factor. And that means you can use it efficiently to convert heat into electricity in the temperature range. This is medium temperature range of about 700 to 500 degrees Kelvin. So to summarize this part, you can start with crystals, and if ferroelectric instability is there, it lowers its thermal conductivity. And if you engineer that ferroelectric instability into inhomogeneous one, you get a glassy thermal transport. So you achieve what we set out as a challenge in the beginning. You had a nice semiconductor to start with. You retained its electronic properties, but you made it a glass in terms of vibrations and phonons. And that's how you get a low high performance thermoelectric. In the last few minutes, I'll talk about another type of instability, which I think is very interesting to physicists. This instability is called as charge density wave instability, which always couples with phonons, by the way. And it involves ideas which are very beautiful. So this is a compound called germanium telluride, which was synthesized by Professor Kanishka Vishwas at JNC. This compound is a layered material, but not like graphene or MOS2. It has very interesting crystal structure. You have basically gadolinium, tellurium, GDTE layers here, which are sandwiched between tellurium sheets. These tellurium sheets are square nets of tellurium, and these are sort of square lattices of GDTE. And electron charge transfers from here to here, and as a result, you get a positive charge on this layer and negative charges on tellurium layer. And now you will see that this is also going to be unstable. That's we showed using first principles calculations that this is the charge transfer. So it's a layered compound where electron transfers from this layer to this layer. And this tellurium sheet is not going to be very happy. If you look at the electronic structure of GDTE3, you have bands which are linearly dispersed bands crossing Fermi energy. And these bands come from square tellurium nets. As you can see near the Fermi energy, all these bands come from the square tellurium atoms which are arranged in the square lattice structure. And if you look at the Fermi surface of the system, you again have a nested Fermi surface with respect to two wave vectors, Q1 and Q2. And as I explained to you, when you have nested Fermi surface, system is unstable. This is something what Pyrals had pointed out long ago in one-dimensional solids. Here we see that happens in 2D systems, and as a result, we get from our calculations, you have phonons which are unstable at Q1 and Q2 wave vectors, which are the nesting vectors. And these are the instabilities. These are phonon instabilities which are driven by charge density waves which are arising from the nested Fermi surface. And the Gruneisen parameter for them is very large. You will see these phonons have Gruneisen parameter which ranges up to basically 20, which is very large. In a conventional solid, Gruneisen parameters are less than 3. And these are measures of nonlinear lattice dynamics, means damped sound wave propagation. As a result, they will have very low thermal conductivity, and that's indeed what is shown experimentally by Kanishka Biswas's group. I will conclude my talk by summarizing that I introduce you to a very interesting class of materials called thermoelectric chalcogenides. These are main group chalcogenide materials. They are characterized by what is called as metavalent bonding, which originates from broken symmetry of metals. They are electron deficient. They involve long-range pp interaction, hopping interactions. As a result, they have very high thermal conductivity, soft bonds, and hence low thermal conductivity, which give rise to excellent thermoelectric performance. And then in the second part, I showed learning from this, we can now engineer the instabilities which are seen here and use ferroelectric phonon instabilities and charge density wave instabilities to tune thermal transport in these materials, which is a major challenge, scientific challenge in design of high-performance thermoelectrics. And with that, I will conclude. I thank my collaborators. Dr. Prasad is a postdoc. Dr. Koendila and Dr. Agya are now postdocs somewhere else. Professor Sienna Rao, who gave us the idea of working on this type of systems, and Kanishka Biswas's group, who did many experiments, and we worked very closely together with him, along with groups at IIT Mandi and ISER Mohali of Ajay Soni and Gautamji. Thank you for your attention.
Thank you, Professor Umesh. It was a very interesting talk, and thank you again for keeping the time. I was getting ready to press the bell, but you kept the time very well. Thank you. So I would like to invite questions from the audience. 1 or 2 questions.
The question is if these materials can be used in a transistor, right? Transducer. Yeah, yes and no. The ferroelectric form can be used as a transducer. Yeah. So those will have piezoelectric responses, which are very large in these compounds.
Yeah.
So
compared to our PGT or these things, as a function of frequency, whether this material can be tuned with the function of the frequency, and it can be used as an ultrasonic transducer to generate the ultrasound or something?
Yeah. So for transducers, they sometimes are not very attractive because of the fact that they have very small band gap, and which means they can have lot of leakage currents. So that will lead to lot of noise in the transducers and sensing type of operation. So in principle, the answer is yes, they are usable, but in practice, I don't think they will compare well with PZT type of materials.
Okay, thank you.
Thank you. The question is, whether the metavalent bond that I talked about in chalcogenides, is it related to coordination bond? And the answer is these bonds are called metavalent because they are intermediate to metals and covalent semiconductors. Okay? As far as coordination number is concerned, they satisfy this very important violation of 8 minus n rule. So 8 minus n rule, which is typically satisfied by covalent or ionic type systems, is violated in the metavalent bond. So, for example, they have 6 coordination number in the rock salt structure, but the number of electrons available for bonding is 1 electron per bond. So, they are electron deficient and they violate the 8 minus n rule.
Hello, sir.
Yes.
It was a nice talk. Sir, I'm an experimentalist actually, so I'm not into the theoretical, not so much. So, as an experimentalist, which properties should we check first to see that this material will be useful for thermoelectric effect? And what are the typical range that we can consider?
Okay. So there are 3 properties that I introduced right in the beginning for thermoelectric energy conversion. Is Seebeck coefficient, it should be as large as possible. Electrical conductivity should be as large as possible. And thermal conductivity should be as small as possible. If you cannot independently control, the power factor is given by S squared times sigma. If you can maximize this and minimize the thermal conductivity, it is going to be excellent. So thermal conductivity, I showed you, minimal means you cannot go below glass limit. So, sorry, see this one is the minimum limit, about half watt meter per Kelvin. This is as low as you can get, not much lower than that.
The interaction is very interesting. But due to time factor, this will be the last question, and there is one question from an online participant.
I want just to know, we know about the energy band gaps in solids and others. You are talking about van der Waals gap. Can you explain briefly what you mean by van der Waals gap? In your graph you show VDW gap. What is that?
No, VD in the last material, right? Okay, I'm sorry. Yeah, I think this is the only material which has combination of van der Waals and ionic bonding. So the fact that distance between these layers is larger than 3 angstrom, is what is meant by van der Waals gap. Van der Waals gap is a real space length scale. For example, if you take bilayer graphene, the distance between 2 sheets is more than 3.3 angstrom, and that's called van der Waals gap. In this case, the distance here is close to that, and that's why it's called van der Waals, but it's not. There is a charge transfer, electron transfers from this layer to this layer. So they are also bonded together by electrostatic interaction. So it's a combination of van der Waals and electron static interaction. Thank you.
So the last question I'll say is from an online participant, M. Suhesh Kumar Singh. So he has asked, can the Grunison parameter be related to photoacoustic effects, that is the generation of sound by pulse light? Should I repeat?
Yes. No, it's a very good question. And the answer is yes. If you look at mode specific Grunison parameter, where you will look at change in the optical phonon frequencies by applying strain. So in some sense, yes, it is related. The polaritons and these acoustic phonons can cross each other, but at very low frequencies. So it will lead to that effect at very low frequency radiation.
I think that must have satisfied the person. And thank you, Professor Wakmare. For those participants who would like to interact more, I encourage that you can interact with Professor Umesh after the session. And for now, thank you very much.
Thank you very much.
So, thank you for your insightful talk. And we are very delighted to have you here. And we would like to present a small gift as a token of appreciation for your presence here. And I request our research scholar to bring out the felicitation.
So the next plenary speaker, I would like to invite Dr. N. Raghumani Singh, BARC, Mumbai. Dr. N. Raghumani Singh is very popular among the Manipur University because he's an alumni of the chemistry department of Manipur University, and he has gone very far from Manipur to reach heights of success in the field of his research. So, main contribution of Dr. Raghumani Singh Ningthaujam is in the field of material science, particularly in rare earth doped nanomaterials and nanomaterials for cancer therapy, including quantum dots. So, cutting short, he has achieved a lot and received many awards and recognition, but I would like to mention just a few, and that is, he is a fellow of the National Academy of Sciences, India. His name is included in the top 2% Indian scientists in 2020, 2021, 2022, 2023, 24, and 2025. He has a lot of recognition and awards. There are 12, 13 of them, so I would not take time by reading out all of them. Just as the President has said, you please look up in the Google and you can see his achievements. So now I would like to invite Dr. N. Raghumani Singh to deliver his talk, Engineering Aspects of Rare Earth Doped Nanomaterials for Light Emitting, Light Harvesting, and Biological Applications. So please. So the talk is for half an hour, Doctor, and at the 5 minutes before, I'll ring the bell to make you.
Good noon, and I'm so happy that I'm coming to my parents' institution, Manipur University. So I did MSc in chemistry from here. I'm so lucky that I'm meeting my teachers and my colleagues, and also coming from the different part of the India and abroad. They're coming here to attend this conference, and I try to give my my work done in the BRC. Mostly I do in the experimental, not in the theory. Just now also work when I given in the most of theory. He's excellent researchers in his field. So I hope that I try to give my best event to my work done in the BRC. Today, my talk is engineering aspect of the rare earth doped nanomaterials for light emitting, light harvesting, and biological application. Hope that this will be similar to what about our topic of this conference will be. I think this will be adjusted. I hope that. So now what are the engineering aspects of rare earth doped nanomaterials and different types of rare earth doped nanomaterials? The application light emitting and light harvesting and the biological applications. What are engineering aspects of rare earth doped nanomaterials? Neurometals have been used in various applications such as light emitting devices, light harvesting, source and catalysis, etc. So even the demand of the materials for biotechnology and chemical engineering areas can witness the economic exponential growth. The doping of rare ions in the neurometal have given additional functional properties due to the optical properties of the rare from UV to BG1 or the infrared range. Their unique magnetic, luminescence, and magnetic properties enable their use in bioimaging, light harvesting, drug delivery, and photocatalysis and sensing. So engineering of size and shape of neurometals of the materials is required for specific applications. So surface engineering is an important step to achieve the advanced materials. In the wet chemical synthesis, growth of the particle is explained by the various processes, including osmotic ripening, mechanism, decrease of surface energy using different specification process. Also, shape of the nanoparticle can be modified through the different routes, use of suitable ligands and molecules in seed-mediated process and proximity effect. Even photon nanoparticle can be prepared by different routes, such as the sacrificing gravimetric reflex methods. So those are, last 20 years in BRC, I used to do this engineering aspect of this nanometal preparation. You see periodic table in the rare earth, you see that scandium, yttrium, and lanthanum, this cerium-2, lutetium is included. Around 17 elements is there. This is very important metals in terms of magnetic or optical metals. See the magnetic properties, so you see spins, you see from change 0 to very high here at the row. But you see the spins, but the effective magnetic moment is changing the time with the elements. It is a very good metals. And this magnetocaloric effect people work in the radar because of this. They have changed the fins, changed the moment with the time very fast. This is one of this. Optical property, you see they have FF transition, this called 4F transition. They have huge transition, they have UV, VG1, infrared region. So this is one wonderful you can see, you can do engineering aspect of this in this rare earth. Okay, so two types of photoluminescence, because I'm most focusing in the most optical metals here. So many people know the down conversion and the up conversion. What is down conversion? Energy absorbed light from in the case of ground state to excited state, or you can take semiconductor, say valence band conduction band, and it goes to some trap diagram, and again, then happen this the emitted light. This emitted light energy is less than of the absorption energy. This is going down conversion. Okay, sometimes people go down shifting. On the other hand, the up conversion cases, what happens is the ground state energy absorbed, okay, sufficient energy, then go to the metasequence phases. This metasequence energy, the electrons, excited state, they have a longer lifetime, so microsecond lifetime. And before coming down, the absorption takes place 10 to minus 15 seconds, very fast. And another electron is hit here. This electron's excited state goes to excited state event. And this gives rise to emission. So emitted light is energy is more than absorption energy. This is one of the up conversion used to do. This can be done mostly out of system. And the frequency down conversion and up conversion, I told you that in the frequency down conversion that energy excitation energy is more than of the emission light. Okay, this is one of these. And this energy transfer, most of the luminescence is actually white open is, particularly and what problem is in the rare earth because of the 4F transition. There's not around transition. Because of the need, because of the emission absorption very weak, we need some supporter or this. They're giving some energy from outside. This is what we call energy transfer process we can do via sensitizer or activator or donor or acceptor light. So sensitizer absorbs the light and emit the light here. But same time, the absorber of the activator absorbs the light in the emitter light from there and the emission takes place. I don't do this, not seen properly, this one, okay. So this is, but when you put it together, so, the sensitizer activator put together, in this transfer takes place, absorbed by the sensitizer, and the emitted light by the sensitizer is absorbed by the emitter and enhance of the activator energy, peak intensity can be improved. Why need ions? There are ions, dwarf, semiconductor, phosphor in the luminescence. So the lanthanide compound, I already told you, this compound, europium oxide, dispersive carbonate, are give a sharp emission peak, but the poor luminescence intensity, okay? And the poor luminescence arises from the forbiddenness of F transition, this capillary structure alone. The poor F transition is very sharp due to negligible effect from the surrounding 5s to 5p6. Okay, but in case of the 3D imminence, the peak is very broad because of the calcium environment. That's why 4F transition doesn't have calcium environment, very negligible. So now, then what happens in the lanthanide ions is really, because of the lanthanide ions, really people drop in semiconductor or insulator. In addition, lanthanide ions in the above lanthanide compound have the poor dominance because of the cross-section between the lanthanide ions, this consequencing effect. However, this forbidden transition can be relaxed by the calcium pin when the lanthanide ions occupy some catastrophic site. Usually people drop few ppm, APM, or few 1 atomic percentage, 2%, so that their dipole-dipole interaction reduce, so the consequencing effect reduce, okay? And also, keep in mind, when you use this system, when the radar stop system, and the semiconductor band gap should be large band gap, around 40-10 electron, because what happening? For F transition absorption emission should not be affected by the similar band gap. This should be in picture when making the radar dop semiconductor or insulator. The advantage of electron doping in the semiconductor is the large number of photon can be absorbed by the band gap semiconductor. During this time, okay, many electrons from the valence band can be brought to the conduction band, many horns are created in the valence band. Electron horn gives rise to emission of the semiconductor, but if emitted light from semiconductor could be absorbed by the nearby dopant ions, emission intensity of the lanthanide is very high because of energy transfer from semiconductor lanthanide ions. This is why we are doping this also, one of the. So this example is the europium 3 plus, very good, because they have the electric magnetic dipole transition, they have soft peak. You see this, they have the absorption process very high in the case of this 395, and that 592 is magnetic dipole transition and electric dipole transition. Okay, this is the one of the 615. So this is very important because this ratio will tell you, this the side is, europium side or radar side is symmetric, asymmetric. So you see for F6 electron, this one, you could make injection. The electron can be rearranged for F, this orbitant can be rearranged. You can have, could be interaction, many energy gets generated because of it. Then then for F 5D something, okay? And then speed oblique coupling can be takes place, and then you can have the many again another discrete energy level created. Again, so start splitting. Even this in speed oblique coupling can be start splitting can be happen. Twice A plus 1, they follow this. Okay. Then you can see europium see many energy level you can see. From that, absorption emission in the inside, in the above and the lower portion can be takes place. This is the beautiful of the lanthanide ions. So this is the Nobel Prize given in the year 2014. The Akashi and the Amano is the PhD student of the Akashi, and the Nakamura, they work in the gallium nitride, blue emitting, light emitting, blue emitting. But you know that they abundant they produce the gallium nitride, but this is blue. But you want to white color, any color, they need rare earth. So this is one of the, the only gallium nitride cannot solve the light emitting error because lanthanide is very important. This side, China is leading in the rare earth. This side, they do zero protocol. This side, United States cannot do anything in China because all rare earth is controlled by the China. So this is one of the we published in the Progress Material Science with my guide, with Gazvi and from IT Kanpur. And this, this one of the, you can see how the, importance of the rare earth. You can find this, I think, Progress Material Science. You see more detail here. And the year is 2014 was Nobel Prize, but we returned, this was submitted. Important of the, gallium nitride in the rare earth in this Progress Material Science. Luckily that same year, the announcement Nobel Prize came. So this rare earth is actually dwarf nanometer and semiconductor. You see semiconductor, you see absorb light, therefore created in the valence band and the conduction band electron goes. This somehow this electrons excited state energy is transferred to the lanthanide ions, then absorption takes place. This is very high electrons going to the electron from this lanthanide ground state to excited state, and some energy happen in the process, then emission occurs here. This is, you see here, This is what I want to say. European bauxite, they have that quenching effect because European, you see this is called as an excitation spectra, but you can take absorption spectra around 20 around, okay? This is arbitrary, but I just take. But when SNO2 drop in the European, you can see the around 100. So this is important that the absorption process can be improved by the doping in the semiconductor. This is one of the. So we published with a paper with the SS Photonic with our Santa, I think from our physics department, from here, and he was postdoc in and some group now is in or Nakanesti. We published together here, you see GD before serum terbium doping system. Serum as a sensitizer and terbium as the activator. Serum absorb light and emit this terbium, this excitation spectra or absorption spectra, you can say. You see this serum absorption is very high cross-section because 4F to 5G transition. Then energy can be transferred to terbium and the energy can be enhanced. This is, you can see, the energy enhancement takes place. I will explain much more. And this can be used. This energy transfer can be used. The glucose sensing, ascorbic acid sensing, means oxidizing, reducing agent sensing. Like this, what do you do? That you keep in mind, serum having 3+ stat, having 4F1, 1F2, and 4F1. This what when you put a KMF4 is oxidizing agent. This serum 3+ sends to the 4+ stat. And then this 4+ stat, when the ascorbic acid or glucose will interact, and serum, they convert to the serum plus state. So what happens is when this without any KMF4 or ascorbic acid, this is the luminescence behavior of the terbium, but when KMF4 putting luminescence almost reduced, and then this again recover again. This we can do sensing. This optical sensing we can do. So in other words, we do from the Manipur University, Professor Rasmussen here. He's sitting and his student, and Faber also was there in the here. You see here, many people say that in the case of the optical matrix, Bernadette or phosphate system, the diagonal phase is more than better than luminescence. But we do that, and Bernadette is they can have two phases. As you know, when preparing, or as a mixture came. One, sometimes tetrachronal phase, sometimes monochrome phase. Then Bernadette, we are preparing European system. Usually, we are getting many pair this phase. This red is actually the tetrachronal, monochronic, and green is the monochronic something. So you see here, we are preparing different something. What a bismuth doping system, monochronic phase is more. Then, but when do the luminescence we do, and still monochronic phase is very better than tetrachronal phase. So it means this is nothing to do any crystallography, because the bismuth absorbed in the UV light, this energy transfer to the europium, this is enhanced. So now we see in the previously, serum is very good sensitizer, and bismuth also very sensitive. Now next step is see how happen this. But when we do this, YPO system, tetrachronal phase system, and when European doping system very good luminescence matrix, and the red emission takes place here. But when the serum doping, luminescence again decrease. This is why it happened this actually this one. In this case, happening when the serum is doping happen this, serum ionizes more of the Y, Italia. So what when this again the compound become hexagonal phase. Because in hexagonal phase, they have pores. Okay, pore like 0H type, some 7 angstrom, then water is sitting there because of luminescence again decreasing with the same amount increase. Okay, it is increasing and this luminescence decreasing. When heated for 100 degrees centigrade, again luminescence again recover because that hexagonal phase water remove again come back tetrachronal phase. This is we publish here in the This is published as it is without any revision. Same thing bismuth doping system. Similar observation we are getting. But here, luminescence enhancement takes place as compared to the serum doping system. But keep in mind how to explain this. We have done many experiments. Just so only few was here. In the suppose we prepare compound in the water medium, the luminescence intensity is very weak. But when preparing in the DTO, luminescence intensity increase because water vibration is around 3,500. And this DTO is around 2,500 something. So the frequency of the phonon is very less DTO medium system. This side, luminescence enhancement happen in the DTO medium. So this is the one where you observe takes place. Now in try to do understood this, what we do that, This actually YPF4 system you see here, actually in pore here, in the pore, this pore is or confined is around 7 angstrom water sitting here. If you keep in mind, when you're preparing in the particles, water is always on surface because, ambient temperature, any water is absorbing. They have 4 hydrogen bonding here. Now, how to distinguish the surface water and the confined water? So what we do? Now, what do we do? How to do? See, this what do we do? And this paper was published from Anna. And you see when we do the experiment, because normally you do the, when you do the NMR, we prove by NMR. The NMR we do why? Because NMR having Brownian motions. If you take any organic compound, anything, they have Brownian motions. Because of the interaction very reduced. But when solid state, because of the, they doesn't have, Brownian motions, they are confined or they attach to anything, okay? Attach to solid. So that you have to do solid state NMR, that's called magic angle, the spinning, then all the spinning, we have to perform this, okay? Magic angle 54.7. And with the spinning, you see that only we see the surface water, but some you can see humps. But when the temperature decreasing up to minus 50 degrees centigrade, this also coming up. Okay, but this was if the spinning is almost nin, and this already remained here. This is called confined water because confined water doesn't phase because it doesn't have 4 hydrogen bonding less. Because surface water having 4 hydrogen bonding, once the 0 degree comes, they freeze. They say the broad peak coming here. Okay, and when the rotation is almost nin, as this you can see here. This we published in this one, and with this year, how we can prove this is we do the facility in BRC, neutron diffraction we do, because neutron we cannot do the water medium, we prepare G2 medium. So we prepare G2 medium, I know explained yes, we do the again, with the simulation about it is, we do simulation. And when the water is no water, what happens is the animal, when the neutron diffraction, how do rise, when water is triangular, how do, water sitting and hexagon, then how the neutron diffraction look like when they put together. After that, what we do, that actually it is, when the water, we do the river analysis with fitting, the hexagonal phase without water and with the water, it is fitting when with the water. This is we have done experiment, and means water is responsible for this. Why water is responsible? Because this is the quenching the luminescence intensity. And sometimes how to prove again, this is the issue like on the phase of this, water here and water here, and we prove by TG studies. You see here surface water removed by 200 degrees centigrade, and confined water is in remained here. Okay, it is confined, P2, P3 is confined water, it's in remained here. This is one of the responsible in the quenching luminescence. And the original work from BRC in Mumbai is, I want to tell you that in that is finding water molecule up to 4 of the rare phosphate in mass spectroscopy. This single water molecule in the pore in the surface water of the particles face the NMR, and stability water molecule and 100 degrees centigrade, and decrease of freezing temperature of the water down to minus 50 degrees, finding of water molecule in the pore and triangular. And another was, I forgot to mention here, and yes, this work is with the Manipur University, here, or Neeraj, Professor Srivastava. We work together in this, okay, this one, okay. So far, I want to tell you, from Manipur, around 35-40 has worked with me, either maybe doing PhD or MSc. I work around 35-40 has worked with me so far. And so now, come to the, again, some of the, I don't know, time, how much time, Madam? Is in time? Oh, 30 minutes. Oh, so time's in there. So now I try to show you that because I want to use biological affections. We need, or biological or display device something. We need film, and it's a solution. See, this is one of his hunters. He's not going to see now, and the Professor Dorendra, his students, and his photo, he's already displayed here. They're done, okay, with me. We published in Downtown Translation, I think, here. So upconversions already, I tell you upconversion. Why upconversion is very important in the imaging system or this one? Why? The upconversion because in the biological sample, we cannot do UV visible. Because our, this we absorb by our body. But if in near fertile regions, it doesn't absorb up to 1 centimeter, 1 centimeter, okay? So we can do imaging because of near fertile using. This is the why upconversion we are coming into my lab. This will be published in one of the, it is here. So this is the compound near infrared, maybe responsive, this one, okay? Composed by the hyperthermia efficacy induced by the fluorescence resonance energy transfer process, which Sony has worked. And this you see here from this, you see how this system of composite system, how they important in the light harvesting something. So you see here, outcome Norfolk, you see here, monosomal Norfolk, we are preparing this, you see, without light, it is almost transparency. With the 90 results, we are excited, we are getting the green emission. The green emission comes from this actually ice and S, this transition takes place from here to here. But this transition S and ice, they have two peaks, one is 525 and 545. This transition is very important, used as a temperature sensor. In the room temperature, you see the 545 is more intensity. When they heated, okay, here, higher temperature heated, this again 525 increases. Because here two peak, this two event, this volume was bit too slow, the electron again go to higher temperature, can go to higher state state. There's an emission occur for the higher energy state. This can be used as temperature sensor. Another this, coming from the green emission, this green emission comes from this red emission. Green emission can be absorbed by the auras no further. They can be heat generated because auras just absorb that doesn't produce emission. Surface plasma resonance absorption and not emit. This can be used as a heating. This is called hyperthermal cancer therapy. We can do this called photothermal therapy, PTT. We call. And the weather. Now I already told you that consequencing effect in the down conversion because of the dipole-dipole interaction of the antennas. But whether the consequencing effect is useful, this question. Yes, it is useful in getting a high luminance when the excitation photon, and this is more than the critical value. This is called photoevidence. In the case of photoevidences, you have to use high concentrations of the activator or sensitizer, something, okay? They have to use. This is one of the, this is not necessarily always time in there, but in the photoevidence, high concentration be used, okay? Gaussian modern can improve another way is the luminance intensity through the energy transfer migration or back energy transfer. This is what we can do. So now we publish one of this in the SS flight, interface with the super bright upcoming sodium atom flight, sodium ERF4 and thorium doping here. You see, ER is putting about, we are putting 99.5 doping, but luminance enhancement very high doping in the 980 laser excitation. You see here, 980 laser excitation, you're getting the red emission enhancement. Because I'm going to explain here, there's a back energy transfer takes place. Okay, the RBM to the again, YB energy transfer, the RBM take to the thorium again to the back energy transfer, then go to the red emitted light here coming. I hope that I believe that so far, I already told you before that you can see green emission and red emission takes place. Here we don't see green emission. I think this is the first report that we don't see green emission in the RBM system because your previous system you can see here, it is green emission here, green emission, okay? But here, green emission almost nint. I think this is the report. I think this is almost around close to 100 citation came. And then thanks to all my collaborators who worked with me in my lab. And this we can use down conversion imaging and also up conversion imaging we do. Very interesting this we have done. I'm going to explain this M7 cancer cell we are using and targeting using the folic acid, we did explain. And this is something we do again, a smart YPO4 system for optic and heating, hyperthermia security in application, this we have carried out. RB620, now he's in Punjab, he's second in Punjab now. And now here we do the temperature sensing, we have done same thing. And the temperature monitored by the this camera, IR camera, we monitor. So temperature can be monitored. And then, another was you see that one of that VRC having facility of the, this radar can be used, for others imaging. Because they are sort of something you can use, either alpha produce, beta produce, gamma ray produce, either imaging or therapy can do. So while we do this system of the Rasmus, my PhD student, he has carried out experiment, this with the upcoming raw part, and we mesophorus silica. You put in here, the mesophorus silica, we put the dots dotted here. You use the chemotherapy. If you do see this porous, yes, you put the, the lutetium, this now in India, PET scan is, now lutetium is now going to refresh. This thanks to the BRC has done this actually extensive work. And because in this, people use other fluorine 18, it cannot, because the lifetime is around 6 hours. Now this few days you can have the lifetime. You can suppose after the the isotope production, you can transfer the many other steps. This routine is the tungsten BRC that PCT has provided all over India. The PET scan now, this is SPECT scan, sorry, SPECT. This is one of the working here. This is SPECT imaging we have done in the BRC, that how the the imaging takes place. And now another was here, lithium doped sodium flight chromium of conversion recently, I think 2024 published. Lucia Gowan, my PhD student here, working here. And this imaging, one interesting that happened is lithium doping improved the luminescence of the chromium by initiation from YB to chromium because constantly improved. I can see the chromium also sending green and red emission can be used. Can you show me this? You can do the video. Can you do the video? Somebody was there? Can you do video? One video was there. You can see three-dimensionally how they the neuroparticles, how they interact with the cytoplasm. So that can be imaging more efficiently by using 980 laser. Can you do? I think, can you do? Okay, I think maybe there, but anyway, you cannot do, then I continue again. But there's an option for 3D imaging. This you see, the 3D imaging can do, and this is beautiful that, how the three-dimensionally, how the neuroparticle and cytoplasm in sand, how interact. This is the green emission and red emission we can do, okay? So it's okay. This is the one of the this our Lucia Gowan has done experiment, and now she's going to submit this next year. Okay. Now, another 2024, again, Lucia Gowan proved how we prove the coarse neuroparticles by optical. This, not only because we are doping, and the core sand, how we can, prove the coarse neuroparticle. She has the platform, and this one, okay. Sure, so less than now. So this will prove by the, this is because when putting the sodium GD tetrabium and serum, okay, how the surface and how to prove by optical means, this will prove by the, redox section something. This is the one proof. Another was scientist Sanathan Devi. She came here, and she walked from the Kumarikan College from here, nearby, only just 15 kilometers. And she worked my lab, and she has performed the experiment. This gone, ultra-low, the concentration of parts per turns with the motor levels detection for the monosonal particles she has performed. Thanks to the madam that she has performed, now she's about close to 60 above. She worked with me. I'm very happy that she has done this experiment and performed it okay. Also, we published now recently this one, prefer that this so far base number comes, not come. Suppose some of the chemotherapy in some of the cancer, it doesn't work. Some breast cancer, some of the doesn't work by the chemotherapy. So that's how we can take on this problem. So my Lucia Gowan and our groups, Nina and Gunjan, and their own groups, has performed the experiment, non-structural of the forehead functionalized highly monosperous symptom doped system for targeting enhanced chemotherapy for human cervical and the triple negative breast cancer. Why triple negative means it doesn't work any chemotherapy, but how we can work this, how the blocking of this, then we work this, published in this one, phase number so not come in the so far. The conclusion of my talk is here. The uses of radar doped particle in different areas are mentioned here, briefly. Meaning example frequency down conversion, up conversion process are provided, and display and light harvesting, and luminance on-off switching, and stability water up to 100 degrees centigrade. And decrease of freezing temperature up to minus 50 degrees centigrade, because we cannot do more than, because enema tube doesn't work less than minus 50, so we cannot do less than. And temperature sensor, and diagnosis and therapy. Imaging through the up conversion process, improve diagnosis and therapy. And I acknowledge that because their support and encouragement is not possible to standing today in front of you. Professor and Chaudhary had my chemistry division, and Sudhita Sakapati, Sandeep, they are working in the most radioisotope system. Their support and the virus can work. To see go on, some of my students, most of my students here I'm showing, others collaborators also, I don't mention here. our Neeraj Luang from here, now is in Pune, Niro Sahu and V.I.D. Berer, now is faculty, and for here in the faculty of chemistry department. And now Okram, I think, I don't know his college, I have no, but I don't know, much more here now. And the collaborator mini Professor last month is sitting here, Professor S.K. Srivastava, I think he was former our department here, also he was BC of the NIHU. And now also BC of the energy, Rakhanu also now. Professor Ranjit, he is sitting here. And with W. Rameswar, and Rakesh, actually Rakesh was in the IIT Dhanbad. We used to do some experiment together, published paper taken in the nanotechnology also. So thank you for listening my talk. Yeah.
Thank you, Dr. Raghumani, for the very enlightening talk, telling us about how the different types of rare earth materials in different concentrations, in different hosts, and with different environments can lead to various kinds of applications. Now I would like to invite questions from the participants. Any questions?
Yes.
Hello, Professor. It's a really exciting lecture. I'm from NIT Agartala, Department of Bioengineering. I have seen one slide where you have tagged the doxorubicins with nanoparticles for breast cancer cell HOPSO MCF 237. Sir, my question is, just I would like to know that how this, it can be used as for targeted delivery for breast cancer cell only.
Whatever we are doing is actually, most of it we are done in targeted therapy only. Either folate receptor or some peptide or antibody, okay, RGT peptides, we use some targeting. So without targeting, we don't do the experiment, most of the biological sample. Sometimes, we block, so the target cannot go. Sometimes this gone, okay, this gone, we gone negative, negative targeting also. So we do that. Most of we are work in the whatever we work, most of target therapy only. Because we don't do specific targeting. Specific target is depend upon size and shape. We can target also, but we don't do because the cancer cells having the vascular that more porousness, so we can do many specific target. But we do most in the targeted therapy here. It's okay?
Yeah, any more questions, please?
Yeah.
Dr. Raghumani, thank you for your excellent presentation. So in the early part of your deliberation, you mentioned about the Oswald ripening mechanism. What is that?
Actually, Oswald ripening is actually, you see solid-state chemistry or solid-state condensed matter physics, anything. What we do, mostly we prepare, the precursor tag and a grinding and heated high temperature, then making ferret, and then heated, then we get a sintering process of that. And this mechanism is a diffusion mechanism theory. This way we call it different, but it cannot apply in the solution system. In the solution system is the difference in something. Oswald ripening is like that. Small size particles can grow higher, larger sizes. At that time, small size particles are sacrificed with a temperature, with a temperature or with a longer time something. So that small size particle sacrifice and larger particle grows completely. This is called Oswald ripening. This is different from the solid state. This is happen, all Oswald ripening happen in the solution system. This is the
More questions? Okay, there is one question from an online participant.
Okay.
M. Suhesh Kumar Singh from Iser Trivandrum.
Okay.
So his question is, it is mentioned about synthesis of anti-cancer drugs.
Okay.
Has any experimental validation study been conducted, more specifically in animal or human subjects?
Yes, we have done the, we have the animal experiment. So far we have done all animal, some of the animal experiment we have performed. Okay, this is, we have proved. I think you can see 2014, we publish paper, many modern. Knowledge, I don't mention, you mention, because BRC you can mention many we have done. If lung cancers, we do the, testing, everything we have done. Because I'm not, because we cannot mention many things for the BRC, we have something, that we cannot mention all everything, but we have many strategy work we have done. We do many others that we cannot explain many things. Yes, anime modern we have performed, even published. Even hyperthermal works we published in 2014. You can see the papers. I think this is the mini modern we published also. Also, we is going to publish some paper in the again, maybe next year, maybe because some of the animals we have performed. Also, even blood tests, blood we have done X-Men, hemolysis, we have done perform, and when this year published also. Some of them we have carried out in the human being, or human blood we take and studies also. So I think this, hopefully that some of them we have done, but we cannot disclose so much in the animal modern because we are restricted in our VRC. We have done this. Yeah.
So thank you very much, Dr.
Yeah.
Raghumani.
Yeah.
And those who are interested to interact more with Dr. Raghumani can do so because he will be present till the end of the conference. That means till the third day. So you're most welcome to contact him and you can interact with him. So for now, thank you very much.
Thank you, sir, for your wonderful talk. We would like to present a small gift as a token of appreciation for your presence here. And I request our research scholar to bring out the gift.
So the third speaker in the technical session 1 in this plenary session, he will not be presenting. He was not able to come. And so that is the end of technical session 1. And we will be proceeding to technical session 2. So thank you so much.
Thank you, Madam Professor Sumitra Phanjobam, for chairing this session. And as a token of our appreciation and gratitude, I request our research scholar to present a small gift to our respected session chair. With this, we have concluded our first technical session. And for the next technical session, may I invite Professor Dorendrajit Singh to chair the session. And for your kind information, tea is being served outside the hall. You may collect the tea and enjoy it inside the hall as we proceed the session here. With that, I hand over the session to our chair to take it forward.
Hello, hello, hello.
So in this second technical session 2, in the plenary session, I am privileged to chair this technical session 2, and in this session there will be 2 plenary speakers. The first speaker is Dr. C. Murali Krishna, TMC Mumbai. He will be speaking on Raman and ACRS point of care process, perspectives and challenges. So, Dr. C. Murali Krishna, Tata Memorial, TMC Mumbai. So, Dr. C. Murali Krishna, FINSTP UK, FRAC UK, FMA Science, FTAS of the Tata Memorial Center, Advanced Center for Treatment, Research and Education in Cancer, Ektrek Nabi Mumbai is a professor, translational research, principal investigator, and a scientific officer at Scientist 8 at Ektrek with primary research interest in the evaluation of laser Raman spectroscopic method in vivo and in situ application under clinical condition. So I invite Dr. C. Murali Krishna to deliver his talk.
Okay. Okay. Good afternoon, and thanks to organizers, Professor Gomti Devi and others, for giving me this opportunity to come all over here. A beautiful place and nice hospitality, and also to two beautiful speakers. They gave wonderful lectures before me. So, with all these things, I will start talking about our ongoing studies on Raman in cancer diagnostics, diagnostics and other things. So, I plan talk like this, with a bit of introduction and then talk about ex vivo Raman for proof of concept, then go for in vivo Raman, where we try to see cancer diagnostics using on-patient studies, then we had to change a bit of gear here to go to minimally invasive approaches. Presently, we are in the evaluation mode. And also, I will talk a little bit about SCRS Raman, which is not really my area of interest, but I did collaborate with some of my friends. I have my own reservations about SCRS, especially for Raman applications. But anyways, I will talk about that because that is also a very interesting aspect of research nowadays. So, all this work, whatever we initiated, started by Dr. Karta when I was in my KMC Manipur, it comes up with a very interesting editorial which says that optics are very, it is like it came in trends in optics and photonics, which talks about the utility of optical methods in diagnostics. Their argument is the conventional diagnosis treatment generally goes by what you call that gross physical and symptomatic manifestation, which are talking about a disease which is already there, probably in the advanced stage. So their idea is like instead of treating an existing disease, can we try to develop a method so that which can be, which can cater to the when the disease is very early stage and treatable stage, when it is really at the very early conditions, at the very primary disturbance, when it is localized. For example, cancer is when it is localized, it's much easier to treat. Can we do something like this? And their argument is if you want to go for those kind of treatments, they say that it's possible to use optics for getting such things. So now my talk, I try to see how much their arguments we could able to demonstrate it with our own studies. So what exactly the spectroscopy does? Spectroscopy, either it's fluorescence or scattering or absorption like IR, whatever it is. What essentially you are doing is you are shining a light and collecting the signal over here. This should tell you what's happening here and what it is picking up. Their argument is that we are picking up metabolic fingerprinting because we are looking at metabolites, which are about 3,000 kind of, compared to quite a few genes or huge number of proteins. So idea is we can pick up this one. So if you can pick up this one, this should tell you what happens in the tissue architecture or morphology or biochemical variations. That's the whole idea behind this study. That is, using light to understand the molecules here, and from there you try to understand what's happening around. So essentially, these variations should tell you the differences between disease to disease progression or disease remission and all those things from the control area. That's the whole idea about this work. And how you work is you collect samples, spectra, and develop methods and you evaluate them and all that. But when it comes to here, so how do we present data? I'm talking, these are all the steps to correction. This goes by the lab to lab. Most of us, we do corrections all over anywhere in the world. But most of us present by scatter plot or by confusion matrix. What is confusion matrix? For example, this is the groups which you are looking at it, and this is the group you are testing. Ideally, all the elements should be zero, non-diagonal elements, to say that you have really identified correctly, you are able to test it correctly. And whatever off-diagonal elements tell you the failure of your system. That means your method could not pick it up correctly or something like that. So this is how we present the data. And next step is how we analyze the data. We analyze the data in two steps. One is, this generally most of us do it. Not only me or any groups in the world, also they do the same. One is spectra-wise data. When you record spectra, each spectra is treated as a independent and this one, and try to analyze them. Or what you call them as patient-wise data. That is, suppose you record spectra of, say, 10 spectra from a patient, and you average them to get one spectrum. Why this difference is, this we do it when we have, say, working on patient. In case of patient, particularly when you are looking at surgical margins or something like that, you will not only identify the control areas, you are also adding the tumor areas. So in that case, it is good to have spectra by spectra. So each point treated separately. When you are looking at analysis on the, say for example, blood serum or saliva or urine or cells, so what you are trying to say is there will be micro heterogeneity in the sample, because like the molecule which you are looking to identify could be in somewhere else. So how do you come out of it? One way of come out of it is you try to capture entire serum and take one spectrum out of it, which is not possible. So what you do is you try to take several spectra here and there, try to average and get a more homogeneous spectrum. So that is what we call as patient-wise data. So when we talk about on tissue or on patient, this is a method. Otherwise, it is this method. That is, say, most of the biofluids and all, this kind of method we try to follow. So this journey started quite long back, somewhere 97, 99, because Karta started. That is more or less time this field of research started working on. Then we had several steps. We started with work on different cancers here, taking the biopsies. At that time I was in KMC Manipur and collected the spectra and tried to analyze data and try to see what happens. This is a stage where we try to see whether these methods do really work. Then went to the next stage where we try to see, can we develop some methodologies so that biopsy can be avoided? That is where we try to see, like on patient can we record spectra or something so that patient can be given immediate diagnostic applications there. Then we went to third stage, that is where, because of certain difficulties I will tell you, which I will talk to you a little later, where we had again go back to ex vivo again. This time, but not biopsy, but we looked for the serum, saliva, and exfoliated cells, urine to look for the classifications. Finally, again, these two, we have a proof it works. Now we are in the final validation, taking the independent. So generally, we try to avoid the operator bias and all that, so we have multiple students working on that. So we are in the last mile run, so that we take it to clinics now. And also, in parallel, we also worked on animal models. So these are some of the studies carried out by animal models. Again, both here also we look for, in vivo, and we didn't use a tissue here, but we did biofluids also on these studies. So I will not go into complete details of all these things because of the time, but I try to give a little flavor how things work and how good or how bad these systems are, and what are the difficulties here. So these are the first instrument what we built up in Manipal. We just clubbed up all these things like spectrograph, then we had a laser here, it will fall on this somewhere here. We put a biopsy there and record spectrum. These are the first few data what we published in oral cancers where we showed it works. Then also we worked on different systems of like for pre-malignant conditions, inflammations and all those things in oral cancers. Then we went to breast cancers and cervix cancers, as I said earlier. So also, we had, in KMC Manipur, we had advantage because a lot of people, like we had surgeons around and they were ready to give samples. So we got stomach, ovarian, and colon, all kinds of tissues. So we could able to work on all those cases. But I tell you one data how it will be interesting. I don't know. Sorry, I don't know whether you could be able to read it properly or not. But here we have multiple cancers and their controls, like larynx, cervix, ovarian, stomach, colon, mouth, and breast, and all these models here. So I said one of the ways is to identify the cancer is, suppose you have built a model, you have tested data, whether the spectra should match or should not match. Basically, if you can see, these are the two conditions. You see only one it matches yes, and all other things says no, it doesn't match. I don't know, sorry, whether you can see anything here. So this is basically, you want to class, when you give diagnosis, you go by both. In one case, it should only match with one model. For example, like if it is a breast cancer, should only match with breast cancers, and should not match with any of the other model. That's how the whole thing is divided. So it's yes and no method. Then also we tried different other methods also of classifications. Finally, yes, we have a method where we know that cancers can be identified, and each cancer are very different type, and it can be picked up. So that is where we try to see how to make it less invasive. One of the ways was to get the fiber, try to take the light to the patient and get it back. So we tried to build up our own fibers to do like this. Unfortunately, this was not a very good way, so we had to go for commercial. We got, this is the HE 785 spectrometer, what we got from Jovinoen. So now the instrument becomes much smaller, as you can see here. All these things are gone. All these things are gone. Now we have only spectrograph, CCD, laser, and this is a fiber probe which they got it. This fiber probe we had to modify again using infotonics. See, this comes with a 5 millimeter focusing lens, so we have to get a 5 millimeter spacer here, so that it can become easy to, while during this, when your recording spectra is dark, and we can't operate on patients. So a clinician who comes to record spectra for us, he will not know how to focus on all those things. So we needed some kind of spacer like this. So the moment you fill it, you know that the moment he touches the patient on his body, we know that he is in focus. So that's how we had to build up this spacer. And also this spacer can be cleaned. Suppose you have 10 spacers, we can disinfect them and use it again and again. So that was giving multiple advantage like that. Then, so these are some of the pictures we have taken during when our first time when the patient came, and how you talk to them and advise them and how to record spectra. And she's the clinician. She's the one who records spectra for us. So now the question is, why is oral cancers are so complicated? We know that oral cancer are common cancers in India, particularly to this region also. But why is that so difficult? Because you can see it, it's so accessible. It's because it's not the oral cancer diagnosis, oral cancer at early stage is a problem. Because here, the patient comes with this kind of situation where there are very small tumors here. This is very difficult to pick up. And this could be micro, that is one thing. And second point comes from because of these conditions in oral cancer. In oral cancer, the major problem is having a second cancer, which can be synchronous, it can be metachronous. So that means what is happening is when the patient eats or smokes, you will have entire mouth has completely got damaged. Now, in one of them advanced to a tumor, this is what you have seen it, this has been removed. But there will be a second coming, and it will come after some stage. We don't know when it will come. So this, during the treatment, clinician will never know that whether anything is coming up like this or not. So these are the two problems. One is, can we advise a patient is having could have a second cancer, you have to be careful. And also try to pick up the cancer at very early stage. These are the two questions we have been asking all the time. So these are some of the studies where we try to identify different cancers at different stages and other things, which I'm not going to all these things. And also, this was a very interesting paper where we tried to show that the earliest changes, that is, these changes can be picked up, which are just started actually. These can be picked up. That's what we showed in this paper. So I give you one data, which I think to impress upon you that how it works. So this, based on these many patients, there are quite a lot of patients, a lot of data. You can see the numbers there, huge large number. So what happens is, in case of mouth, we have tongue, we have lip, we have buccal, and all those things. Should this be treated as different models, or should it be treated as same? That was one question we tried to ask. That is to identify anatomical differences. What we noticed is, in early stage, yes, there are some variations. But as you keep on going towards disease conditions, they don't have any variation, whether you pick up from tongue or whether you pick up from buccal or lip or something. All cancers look same. So at this stage, what we thought is, there is no point in developing a great model for all different sites. We can pool all the data and put up this one. This is one study. We can tell you that, see, these are all controls. These are all the disease conditions. The crosstalk is almost minimum. It's almost maybe 1%, not even 1%. So we can easily classify healthy as healthy without any problem. That is what is the present status of it. And also we can also identify the second tumors. For example, there is a patient came, we recorded spectra on control side, we also recorded on the tumor side. Then the spectra, in some cases, we see there is a match between the tumor side versus control side. When we see those people, those patients are more prone to get a second cancer. That's what we have demonstrated. We can tell them much in advance. You have to be under regular checkups, or you have to come regular follow-ups, so that this can be avoided. And also we can also identify surgical margins. But generally surgical margins in head neck is not a very difficult thing to do it. Generally they just remove 5 centimeter around, so they don't bother. But in brain tumors, they are very important because we don't want to lose some of the neurons and missing things. So surgical margins can be given, but it's not very important for the head neck cancer at this stage. So we also did on cervical cancers. And here our question was, how can we avoid colposcope, and how we do in camps? Is there any way that we can have a quick diagnostic or quick screening tools? Yes, we found a way to do it. For example, we have a control. When the spectra of control and cervix are same, that means patient is fine, otherwise is not fine. So we could able to go to that stage. Well, at this stage, we have to change our gear and we have to go back to serum and saliva and all those things. I tell you a little later why we have to do that. But this is a very interesting idea where you can just, this is what we picked up actually. The earlier mission, whatever we had, we tried to convert into a kind of a fiber probe, microfiber probe, and try to work on that. It worked well. We could able to study all kinds of concepts, for example, like pre-malignants, malignants, and also the possibility of identifying a person who can have a second cancer. How we do it? We record spectra of serum at the time of before surgery, while he was discharged. So by looking at these two cases, still we could able to pick up the cases who come back as a second cancer. We could able to pick it up. That I will show you the data a little later. So this one data where we try to have all different groups here and try to classify. Our classification of controls is 83%. That's very good actually compared to as far as good screening tool. Compared to the current screening tools, it's very good. And most important point is this. We had another disease, that is a brain tumor. So we have one brain tumor and other tumor from the mouth cancers. Both can be classified very comfortably without much of overlapping data. So that is where we are now. That is, we can not only identify a cancer, also different type of cancers if possible. That's what we are at this stage now. Then we went for the next stage of looking at the cytology. The reason is there are some questions people asked. Maybe serum is a very dynamic sample and multiple things can affect it. Why not try something bit different? So that's why we went for the less invasive than biopsy went for the cells. We scrap the cells and spin them down, record spectra and get its cytology done, and it works well. We have shown it in cervical cancers, we have shown it in oral cancer, again all 3 steps, even prognostic applications we have done. That is, we take suppose control and the tumor site, if the spectra match, those patients will have a higher opportunity chance of getting a second cancer in due course, so they should be warned about it. So, but what made me very interesting about is this data. These are the data recorded from squamous cells of head, necks and cervix. And for a typical cytologist, squamous cell is a squamous cell. It doesn't matter where it came from. It came from cervical region or it came from mouth. You can't differentiate. But by Raman spectroscopy, it's possible to differentiate both squamous cells by their origin and also by their what you call the pathological condition, control versus tumor. That can be picked up. Because we are not looking at the, what you call that, morphological changes, but we are looking at molecular variations, so we can pick it up. That's the idea we have. And also we are looking at saliva. Saliva is a very interesting sample because it collects, it's very close to this mouth cancer, so it can be picked up. So this was the idea, we tried to look at it. And we tried to see whether to take saliva as such, saliva dried form, is it supernatant by spinning it, or the pellet, all these things we try to do it. And our suggestion is, don't go for any of the modifications, just use it air dry. Just put a sample, few microliters on the calcium fluoride window, dry it for a minute and record spectrum, that's better. No need to do any other modifications, it works well. We have very good classification with control versus tumors. So we could able to see the tobacco variations, we could pick it up, all these things. And as I said, one of our interests is to, can we suggest a patient that will he get a second cancer or not, and how serious he should be about his follow-ups. That we have demonstrated once, somewhere around 2015. Again, recently we demonstrated, looking at the samples, and this case, they were followed for 2 years. This, they are followed about 8 years. So we could able to pick up, we could able to tell them that, yes, this is based on the sample collected after surgery, that is when the patient is being recharged. The idea in this case is, if there is a small tumor, you have removed major tumor, so still the second tumor, if it is little bit here, the microtumor, still you should shed some kind of molecules that should come in the serum, so you can pick it up. That cannot be picked up before surgery because already there is tumor, you can't pick it up. But after surgery, definitely we can pick up. It works very well. This is what this data talks about to us. Now we are validating it further based on another 500 patients. We should have data coming up soon. And other thing also, what we did is hamster models. Here it is control, somewhere here it becomes tumor. But at what stage we can pick up, there is a modification. That was the idea. 4th week or 5th week or something. The reason for this is, 1 week in animal is 1 year in human being. And typically in human, most of these cancers take about a decade to come, decade to visualize to us. So can we pick up somewhere in the early? That was the idea. So this is the different stages where you see the tumors coming up. And we can classify the cancers using serum as early as 4th or 5th week. That means much before tumor really appears, can be identified by the visual, we can still pick up. That's the idea actually we have right now. And also what we see is, next thing is, when you see here, sometimes when the tumors appear, they appear in big numbers, sometimes they appear in small numbers, depending on how it is applied. Now the question was, is there any limitation on identifying by serum using the tumor? That is called tumor load. If the tumor is big, is it easy to pick up? If the tumor is small, is it easy to pick up? What happens? That was the idea. So what we noticed is, it doesn't matter as long as there is a tumor, whether it is a small tumor or a big tumor, we can pick it up. Why this is important for us is, our argument in looking for the prediction of a second cancer is based on there should be a microtumor somewhere and we are picking up. So this gives a confidence to us, yes, As long as tumor is big or small, tumor is present, serum gives some markers, and Raman spectroscopy can pick it up. That's the kind of confidence what we have right now. And also we are also working on animal models. I told you that is the hamster approach. This is basically we are working on canine cancers. These are the canine pet dogs which come for treatment. And in Mumbai we have a cancer center for treating canine cancers. And canines have very close to what we have. All diseases are very close to us and their behavior is very similar to us. So, and also give multiple cancers. One slide is missing here. The canines will have a lot of cancers. Unlike us, for example, in mouth cancer we get only squamous cells. Whereas in canine, there are a lot of tumors comes. So is it possible to pick them up separately? That was the idea what we are trying to look into this. And Pradeep is the person who handles the cancer care of animals. Yes, we can able to, here at this stage, the number of cases what we have worked on, yes, we can able to definitely pick up a cancer, canine versus non-cancer condition, different cancers can be picked up. Success rate is about 85% and above. So far is a good thing. Now we'll talk about little challenges. One challenge is what happens, the instrument conks up. You build an instrument, you got data, you have spectral models, built everything. But you know that spectra depends very much on how the instrument is built. So how it happens. Is it possible that you can transport the data from one instrument based to other instrument? For example, like we work on head neck more, whereas people like in UK, they work on more on prostate. How we can work, how we can use all this data and work on that. So this is one thing which we are trying to look at it. Second point is we keep on saying that we are picking up identifying a biomarker and stuff based on a biomarker. Now the question, if it is a biology person in the crowd, they will ask you, which molecule you have picked up? Can you tell me the name of the molecule? Unfortunately, we don't know. Now we are trying to work on that. And I kept on telling you that why we shifted from, say, in vivo to this one is the problems with the probe building up. Probe building is not so easy. The first probe worked very nicely. The moment when we went for this kind of probe, from this probe to this probe, when we are working on cervical cancer, we had a lot of problems getting additional lines and stuff like that. And also there is a limitation in the probes. So that one speaker is missing, so I get a little more time, no? I thought one speaker is missing, so I will take a little more time to finish off. Right? So, this is the hollow fiber system which we are trying to build up. If this fiber comes, all this damage will go. That we are working on that. And also data transferability, this is one study which people try to identify what are the problems with the data that we are trying to work it on. We built up some, what you call this, augmentation and all those things, and we could able to pick up. Yes, it works. Now I quickly talk about SARS. SARS is a very interesting topic because it can go, one of the difficulty of Raman is, conventional Raman is, it's, the signal strength is very weak. By SARS one can pick up. You can see here, there is no signal here, you can get a very good signal here. There is no signal here, and you get a good signal here. So SARS is very useful. This is basically colloids. But my problem is getting a reproducible nanoparticles, I think is a problem. I think some of you in the crowd knows. You are from material science people, so you know it better. So we had one Mexican program we had to do because I had to get into this program because this ambassador sent me quite a few letters to take on this project. So eventually we did it. And we found, yes, it works very well. We could able to do quite a few things like different nanoparticles can be used to, kill the cells and other things, which our previous speaker was also talking about. So one point which we could able to solve is this imatinib B. What else happens with imatinib B is, this drug is a first line drug for the CMLs, and it should be at least 1 microgram per ml so that it can treat. But to do that, how much drug we have to put into the patient? Based on the patient clearance, sometimes we may have to give more, we may have to give less. How do we identify? So we built up the SCRS-based method to pick up this one, which fires at 1 microgram, so we can pick it up. So this I'm not going to, because there was a earlier talk where they showed that, like how nanoparticles can affect. So another point, what I'm trying to tell you is that nanoparticles preparation was a problem, but can we do a nano patterns? Yes, we did a nano patterns, and we could able to do all these things, and we could able to classify them. For example, here, we could able to get breast cancer cells can be differentiated, and also we could able to see the imatinib B up to 10 microgram, we can pick it up, and things like that. We could able to do that. Well, so only change here is, earlier I used to put this in red color, now I'm putting into yellow. Simple reason is, now we are in a position to take it to clinics, because we are starting a large program, and we are going to be able to pick it up now. So this is my bunch. Thank you.
So, Dr. Murla, C. Murali Krishna, he has given very good talk on the application of Raman spectroscopy in the oral and serum Raman spectroscopy, etc., in the detection of different type of cancers. And interesting thing is that detecting early cancer was a problem. But here he is mentioning about early detection by using the Raman spectroscopy. It is a very interesting, nice talk. And if you have any question, 2-3 questions, so you can put your questions.
Yeah. Can you just throw a light on how the spectra of the tumor is orienting along a particular direction compared to the healthy spectra? In one of the slides, maybe around 9 or 10, you have shown, because you are performing the PCA, that is a principal component analysis, and your spectrum is orienting along a particular direction in the tumor compared to healthy.
Where you could find out actually? I couldn't see.
Maybe around 9 or 10 at the beginning.
This one?
Yeah, before that, yeah, previous one. Yeah, this also okay, previous one. No, previous?
This is the tumor area basically. This is control area.
Previous slide? Yeah.
Here, this is tumor.
Healthy region, it is like forming a cluster in some sort of circular.
Yes.
Whereas in the tumor, it is orienting some diagonally in a particular direction.
Actually, this was a very good question you asked actually. The purpose of this work is different actually. This is to see how different sites work actually. That was the idea. This is controls. And all controls. Okay? We are not looking for the tumor here. We are looking for all controls. All controls from, say, buccal tumor, lip tumor, tongue tumor, all those things. Okay, it's those conditions. So, in the beginning, because their collagen levels are different, so they should be different. Right? In the beginning, yes, they are different in the healthy. The moment you go to contralateral, that is opposite side. Suppose there is a tumor here, you are looking at here. Tumor here, looking at other side. When you record spectra there is already slight modification. That is why whatever you see the classification here, drops here. Okay? And pre-malignant, still you see some kind of variation based on the site of the disease. Not the disease, site of the disease. But the moment you go to tumor, there is no variation. Everything is lost. There is no lip tumor, there is no buccal tumor, there is no tongue tumor, all tumors are one and same. So that actually taken to us, go for combined analysis. No need to build a model. For example, I record spectra on tongue, say 50 patients, I build a model for them. I build a model for buccal, that need not to do it now. Now one model for head neck cancer will work. That is the purpose of this work.
So the next question is, compared to normal like MRI or CT scans, what is the difference from your Raman studies?
I tell you, I take back to my first slide.
It is a non-invasive, okay?
I tell you. Give me a little bit time. So what you are talking about is this. When you go for CT scan, you are talking about a disease already existing. We are not interested in that.
Yes.
Our interest is not for diagnostics. Our interest is to screen. Okay? Screen when disease is not is visible, can't be picked up by clinician. That is the stage we want to pick it up. So that is possible only by biomolecules, not by this one. Yes, Joe.
Hello? Yeah, I would like to know, because you have just shown the saliva spectra. Can you show the normal saliva spectra and the cancer spectra? So how, say that normally I would see, the difference is very small, no? How can you just show, so it is a malignant, say saliva?
That's why you use PCLDA, as simple as that. You can't make out. That is one of the reasons why we had problem with biology people. We can't tell you what is a molecule, right?
Yeah.
So generally what we have noticed is, there is a enzyme in saliva. I am not getting the name of it. When you eat sugars and all, you feel that is the enzyme. That gets damaged, lost. That is one thing we can pick it up. Okay? So that is minor protein variations can be seen from saliva to normal saliva to disease saliva. We can pick it up. But success rate is not good. Success rate is less than 70%. Let me be honest with you. Okay?
Yeah.
That is the reason when I mentioned, I talk about serum. It works well. Saliva doesn't work very well. Especially we had a problem with saliva when you take tobacco. See, your interest is to classify a smoker versus smoker or a tobacco user versus healthy person, cancer person. Because those are the people get cancer. It's not a healthy person getting cancer. It is a habitual getting cancer is more common. There your success should be very high, but there we are not doing great. That is a problem with saliva at this point of time. So I don't advise you to go to saliva at this stage. And saliva is extremely dynamic. It depends on what you eat. It changes by hour. Okay? So getting a proper sample is difficulty in saliva, which is not that difficult in case of serum. Serum is dynamic, but early morning serum can be picked up. That should be good. But in case of saliva, it's very difficult. If you brush, you get 4 red lines. That's a problem.
Did you try for SIRS mapping?
No. SIRS, I'm not comfortable with SIRS. Because I find problem with SIRS is nanoparticles may not be reproducible. I know that most of people don't like my language. That is a problem. Second is, already you are working in a gray area and you are adding more gray to your area. And my interest is to give a proper direction to clinician. Yes, there is a cancer, yes, pick it up.
No, I have seen so many papers, depending on the size of the cell, you can able to find out the SIRS mapping. Based on the thickness of the cell, you will easily find out.
No idea, I am not. SIRS actually, Professor Gomti Devi asked me to talk about it, so I added some slides. But if you ask me, I'm a pure Raman guy. I like to do only pure Raman. Okay. Not even cars and all those things, because that add to the complications. So when you read biology, when you are not using a model, you are using a patient-based, that comes with a lot of baggage and of problems already. So you don't want to add any more problems to that.
Okay, thank you.
That is my limitation there.
Related basic question is how it is very difficult to get normal Raman spectrum of serums.
No, you can get it.
So how do you get it without using any nanoparticle?
No, you can get it.
You get it with which laser? Which laser you are using?
No, you get 532, 785, 632 everywhere.
With all? Okay.
You get. But only thing is, see, what you should do is, you need about 30 to 40 microliters.
30 to 40 microliters serum. That is available, but it is difficult.
No, with the instrument, for example, Vitec is a good instrument. Even my one, which I set it up, what I used to do there was I used to drop by drop.
Okay, that equipment may be dedicatedly fabricated for that.
No.
Is it normal?
No, it's normal instrument. Nowadays, instruments have become very good.
Okay, I accept it. Sir.
No, instruments are good now, you can pick it up.
Hello. Hello, sir.
Hello.
It's really good. Exciting lecture. Sir, last third slide, you have mentioned one spectra, Raman spectra versus plasma concentrations.
What is that?
In cancer cells.
Where?
No, last slide just beyond that. So,
Hamsters, animal, what is that you're talking about?
no, last.
This one?
No, before that, please. Back, sir. So, thing is that, sir, you had mentioned that drug concentration, plasma drug concentration through the Raman spectra. So, my question is that is it possible to measure the protein drug interaction, or do you have any information regarding pharmacokinetic profiles of this drug?
You're talking about imatinib B?
Yes.
No, imatinib B, actually the problem in this case is, it's in serum what we are picking up right here. What we did is, this is serum data, serum spectra, how you get it. This comes from the nanoparticle, okay? So what we associated is one particular line, which we thought is coming from imatinib B, which we picked up just by imatinib B alone, okay? From there we could pick up to say that, if you see that particular line, you see this line? If you see this particular line, that is imatinib B. And that concentration we have verified, it is a spiked one. Serum is taken, 1 microgram of imatinib B is spiked. It's not, it's a...
Any processing was done, or it is just simple?
No, it's on the nanoparticle. This is nanoparticle, SCRS. This is SCRS. This is what you call dry coating. As Professor Ranjit Kumar was asking, earlier when the instruments were not good, how we used to record spectra is you put a serum drop and wait for the serum to dry. When it dries, it makes like a cup. You put it, at the edges you made a ring and start recording.
Means at which dosage form drug was given, and after that, how long time after you have?
No, it's not, it's a simple, it's not a realistic study on the patient, no. It's a drug was spiked into serum. It is to demonstrate that we can pick it up. Serum is taken, in serum, you put 1 microgram imatinib B, mix it, and record spectra to show that that particular line can be seen. Okay, it's not realistic. You got it?
Let me go to the next online question from Dr. M. Suresh Kumar Singh. His question is, what is the state-of-art non-destructive scanning clinical technologies considered to be the best in clinical setting for mouth cancer diagnosis and therapeutic treatment? Are the endoscopy-based imaging technologies not exploited or are not helpful?
No, actually, in mouth cancer, the issue is mapping and all not required, because you can see, open the mouth, you can see. But the only problem comes is, the question what you asked here is, when the tumors are very small, can we pick it up? And people did try. There is a well scope, there is other missions people try, but they failed. I don't want to talk about it. There's a fluorescence-based method. People tried to take a picture. So at this point of time, we don't have any instrument to pick up a small tumor, and that is the first thing right now, which is cheaper. Second point is we have a lot of smokers, and these many smokers, how you treat, how you scan everybody, right? It's millions of people. That is the difficulty. So if you can get a serum based or saliva based, it's easy, because you just get a blood sample and done easily.
Let us thank Dr. Murali Krishnan for a nice plenary talk.
Thank you, sir.
Please. So the next speaker is Professor Ranjan Kumar Singh from Banaras Hindu University, Varanasi. The title of the talk is Application of Raman Spectroscopy in Biological Molecules and a Liquid Crystal. Professor Ranjan Kumar Singh is MSc, is from Patna University and a PhD from Banaras Hindu University, Varanasi, India, and a postdoctoral fellow with Professor Wolfgang Kiefer as ABE AIDS Fellow in Germany. Current research interest is to study metabolic processes, reactions, liquid crystals, and liquid crystal-based sensors through spectroscopic, Raman, ACRC, IR, UV visible, and steady state and time domain fluorescence technique, and DFT. So I invite Professor Ranjan Kumar Singh to deliver the plenary talk.
Okay. So, thank you very much to Naumita and Gomti for inviting me to this conference. And I am just previous talk was on high-end application of Raman spectroscopy. And my one is little bit basic one. So let us start. And I am already 10 minutes late. So sir, please give this time. Okay. So every year Raman spectroscopy we got Nobel Prize for an Indian scientist for the work done on Indian soil. Therefore, I want to give 2 minutes to Raman. And we every year we celebrate Science Day to commemorate the discovery of Raman effect, which brought us Nobel Prize. And these are the landmarks in the Raman. Okay, so can I take this one? Can I take this one? This one, no? Okay, I am very much. Okay, sir. In physics, there are many discoveries which are accidental, but the Raman discovery was not accidental. It was a well thought discovery through competition worldwide. Let us look at Compton Rayleigh scattering was already known. That was elastic scattering, and Raman started working on optics in 1921. In 1924, Arthur Compton discovered inelastic scattering X-rays, which we are teaching in our undergraduate classes. Then people started thinking that if inelastic scattering is in X-rays, why not in optical region? Raman also thought, many other scientists also started working on it, and you see in 1928, Landisberg and Mandelstam independently observed the inelastic scattering of light. On 21st February 1928, Raman on 28th February, but Raman could publish earlier on 13/4, and we got Nobel Prize for that. Okay. After the discovery of Raman effect remained dormant. It was not so much useful as you just saw in the earlier slide, earlier talk. It remained dormant till 1960 when laser was fabricated. After the fabrication of laser, it gained momentum, and you see in earlier days the PMT, photomultiplier tube, was used as detector. That was very slow. Then CCD was invented in 1980, and it was used as a detector in Raman spectrometer. Then many other things were discovered in 2018. You heard the news that there was one Raman spectrometer attached to the Mars mission. There are many, after the discovery of laser, there are many variants of Raman spectroscopy, and these are the non-linear Raman spectroscopy. Above 2 is linear, and other later on are non-linear Raman spectroscopy. So just there are many students here, so just to know what is Raman process. In fact, if a molecular system, a monochromatic light falls on a molecular system, h nu 0, then in the scattered part you have reduced, increased, as well as the same frequency. The same frequency is the Rayleigh scattering, and reduced one is Stokes, and increased one is anti-Stokes. With the energy level diagram, we can understand it. V0, if the scattering starts from V0 state, this is Stokes, and if it starts from V1 state, this can be anti-Stokes. In both these Stokes and anti-Stokes transition, the transition is from V0 to V1 state. So same information can be taken, but the intensity of Stokes part is more. Therefore, in experiment, mostly Stokes part is recorded, and 0 to 1 transition in vibration case, 0 to 1 transition is recorded. Okay. So the scattering time scale is 10 to the power minus 14 second, and it is quite smaller than the fluorescence time scale, that is 10 to the power minus 8 second. Okay, in experiments, what we have to care for is that in normal Raman scattering, the excitation source should be much lower than the first excited electronic level. Okay, Raman intensities depends on Raman scattering cross section, excitation frequency, incident beam irradiance, number of molecules in the target area. Raman scattering is a very weak process, and we can just have a look that how weak it is. You see, the fluorescence is 10 to the power minus 19 scattering cross section. For Raman, it is 10 to the power minus 29. It is so small cross section that we need high power exciting source, that before laser it was not useful, and still with lasers, we need many other techniques like surface enhanced Raman spectroscopy for many applications like biological systems. And if we change the laser, we can also change the intensity for high frequency lasers. The intensity is more because scattering process depends on nu to the power 4. Okay, these are the standard techniques, which the standard positions for the different vibrational modes which appear in Raman. They are used for the analysis of the Raman spectra. And for biological system and many other systems, we use surface enhanced Raman spectroscopy, where we use some nanoparticle in colloidal form or in other form, and the analyte molecules are adsorbed on the nanomaterial, and the intensity of Raman bands, certain Raman bands are enhanced. Like you see, this is a normal Raman, and this is the source of Mikhail malachite green. So this source spectrum. Okay. Now, with this much of background, I want to take few examples to to cover the area of this conference. So these are the medical applications and environmental applications. So I just come whenever you get Raman spectrum. It is like a Raman band. So we define 3 parameters, standard parameters: nu zero, FWHM, and integrated intensity. And physical the quantities are associated with these parameters, and we can see that wave number shift is actually gives the nature of interaction that can be attractive, repulsive. Line width is associated with the dynamical properties, and intensity is associated with the molecular association. Now, if we observe this Raman spectrum, is it the intrinsic Raman spectrum of the sample, or there is anything added experimentally? So answer is that something is added, and that is because of this slit. For any spectrum, we need to open the slit to certain amount, depending on the requirement of the intensity. So in order to have see it, it is not focused a bit, but anyway, you can have an idea. This is the Raman. This is the Raman spectrum of chlorobenzene, 2 bands, and the same bands at different slit opening. Slit opening is larger as you go up, and you see the line is broad. If you take this line, you have different result. If you take this line, you have different result. Means the effect of slit is there, and we need to remove it, and there are methods which can be used to remove this slit effect, and that work I did during my PhD, how to remove the effect of slit width. And then Raman lines is also polarized. Many physical quantities can be associated with the polarization of the Raman band, and the polarization of the Raman band is associated with the symmetry of the molecule. Likewise, for liquids, what we can do, we can measure the parallel component and perpendicular component just by keeping the analyzer and polarizer parallel and perpendicular. And we see in case of CCl4, you see when they are parallel, we have 3 band in this region. This one is CCl symmetric stretching mode, and if they are perpendicular, this band is completely removed. So this much effect has has the parallel and the effect of the Raman line is polarized. So this polarization can be studied in many cases to understand the physical properties. Now, I come first example of example in hydrogen bonding. This is the widespread, this hydrogen bonding is widespread in nature. In all kind of biological system there is hydrogen bonds, and Raman gives very good signature of the hydrogen bonds. For example, you can see this is chloro, this is phenol, and phenol, ring breathing mode of phenol, and phenol has two components, one this. So because because of the hydrogen bonding among the phenol molecule itself. So in order to see it, we can mix it with some other molecule like acetonitrile, and we can see that as the acetonitrile is increased, the acetonitrile molecule diffuses in the phenol, and the hydrogen bonds breaks, and therefore this in the intensity of this hydrogen bonded network reduces. But at the same time additional bond is formed between phenol and acetonitrile, and because of that a new band appears. So if it is happening in phenol, then it should also be seen in acetonitrile, and you can see this is the C triple bond N mode alone, and this is due to hydrogen bonded C triple bond N mode. So this is the hydrogen bonding application in hydrogen bonding. In case of phenol plus benzene, there is no interaction, and therefore this band removed, but no new band appeared. This one is this band is due to benzene. Okay, now we come to liquid crystal. This is also a very smart material, and in liquid crystals, Raman spectroscopy has very precise use in detecting the phase transitions in liquid crystals. We can see here how precisely the liquid crystal transition can be detected with Raman spectroscopy. This is one liquid crystal material, and this is temperature dependent Raman spectra of liquid crystal, and you can see this is sharp shift of bands at liquid crystalline transitions. So now we come to environmental detection, and we fabricated a liquid crystal based sensor for detection of hydrogen vapor. For this, I just in brief I tell it that hydrogen detection is done by 5 Cb. This is most common liquid crystal, and 5 Cb is doped with another liquid crystal that selectively binds with the hydrogen vapor. And now you see the glass slide, piranha treated glass slide was dipped in DMOAP surfactant, and the surfactants are attached in this way, and and then the 4-deoxybenzoyl 4 dBA was 5% 4 dBA was added to the 5 Cb, and this mixture was dropped on a copper grid, TEM copper grid, and then it was kept in crossed polarizer. When 5 Cb and 5 Cb doped 5%, the texture is dark because the molecules are aligned like this. And when hydrazine, it was exposed with hydrazine vapors by 500 ppm, 300 ppm, 30 to 500 ppm, then it becomes bright, 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 bright. And we could observe the hydrazine vapor up to 30 ppm. So luminosity is also plotted. And what is the reason behind this bright textures? Because hydrazine with 4 dBA makes a diimine, and because of this complex formation, the alignment breaks, and due to breaking of the alignment, the bright texture appears, and we can detect the hydrazine vapor. If diimine is formed, then of course the signature should be available in the Raman measurement. Then we measured the Raman spectra of 5 CV plus dBA, 5 CV plus dBA plus hydrazine vapor, and 5 CVA plus diimine. These are common to this, and it is proved that 5 dBA is, diimine is formed. So, upon exposure, this is the conclusion of this part, means the liquid crystal was used to fabricate a sensor which can detect hydrazine vapors. Now let us come to second example, that is in medical science. We know creatine and creatinine. For kidney disease, we doctors measure level of creatinine and level of urea. So the creatine is another material that is stored in muscles, and that is converted into creatinine. Can this reaction be initiated in the laboratory, or can it be reversed? So in this study we have done this work. Creatine conversion. So after this Raman study, we in vitro cyclization of creatinine and creatine, rates of cyclization is a function of both temperature and pH. And presence of 3 microscopies. Creatine protonated dominates at low pH, and zeta ionic form dominates at high pH, neutral form in traces at all pH values. So with the Raman time series Raman spectrum, we could detect the 3 forms of creatine and the conversion from creatine to creatinine was observed. It was also theoretically proved. It was also proved by theoretical calculations that the presence of all the 3 components. So the same thing. So the formation of protonated species and deuterionic form in the initial stages of the reaction due to excessive proton concentration in acidic medium, and the gradual cyclization of the protonated species to yield creatine is evident from Raman spectral data. So we did the experiment at 3 pH. Out of the 3 pH, we found that at pH 3, the conversion is faster. And ring formation occurs much faster. Okay, now if from creatinine is formed, this reaction we could observe in laboratory. Can it be possible to observe the reverse reaction? Yes, it is possible, and that can be done at basic pH, and we also did it, but creatinine is not soluble in water. Therefore, it was difficult to initiate the reaction. Then what we did, we tried search spectrum, And for SARS, of course, silver nanoparticle was created and the SARS calculation was done. And it was found, I come to the result, I come to the result that, that this reaction was initiated, and it was observed that at pH, basic pH, the creatinine can be converted into creatine. Higher the pH, faster is the rate of conversion, but at the same time, reversibility is also more pronounced. Okay, now next example is leflunomide to teriflunomide. This also we tried with the surface enhanced Raman spectroscopy. A drug, what we take, actually it is absorbed in its metabolite form. For example, leflunomide is a very common drug, and if we take it orally, then it is it metabolizes to teriflunomide, which is absorbed in our body. So this conversion was studied through surface enhanced Raman spectroscopy, and we found that at basic pH, this conversion rate is faster. Higher basic pH, this conversion rate is faster, and if and we in fact suggested also to our hospital that if it is administered with antacids, then it is possible that effect is faster. So this is the Raman bands, characteristic Raman band of the leflunomide and teriflunomide. Now, in our most recent study, we have detected the quinolinic acid at very trace amount. For this, the quinolinic acid is a neurotoxin, and its concentration up to 100 nanomolar is in physiological condition, because it is present, but when it is raised to 10 to 40 nanomolar, then it is a disease condition and creates many kinds of toxicities. So in order to observe to how small amount can we measure with surface enhanced Raman spectroscopy, we tried SARS with nanocolloidal solution, and we prepared Ag nanoparticle and performed SARS. So Ag nanoparticle was prepared in our laboratory, and then it was characterized. Of course, these are the standard characterization techniques, TEM and XRD and DDAX and UV visible and Raman. These are the standard techniques. We did it. And SARS, then the SARS substrates were tested for standard standard material mercaptobenzene, and it worked up to 10 nanomolar concentration. Then the same material was, the same substrate was tried, was used for the for detection of quinolinic acid, and we could detect up to nanomolar concentration, up to nanomolar concentration. These are the characteristics modes, because specific modes need not to be discussed here. So, and at the same time, the pH also increased as the concentration of quinolinic acid is decreasing, pH increasing. Means what we observed that quinolinic acid is present in two forms, in neutral form and deuterionic form. At concentration, these two, that's two lower concentrations, quinolinic acid remains is present in deuteranic form, but at the concentration lowers in this region, it is deuteranic form is converted into normal form. So these are the two neutral form of quinolinic acid and deuteranic form, and we also verified it by theoretical density functional calculations. This work was just recently published in Journal of Raman Spectroscopy, and then the interaction with human serum was also studied with the quinolinic acid, and we found that in human serum also at lower at up to 10 to the power minus 4 molar, the quinolinic acid in deuteranic form, and above and below 10 to the power minus 4 molar, 10 to the power minus 5 to 9, it is in neutral form. So this work was published recently. So this is the conclusion, what this work recently published in Journal of Raman Spectroscopy. So I am thankful to these people because I have to finish it. These are my from abroad my AVH Foundation, AVH Fellowship Advisor, Professor Wolfgang Kiefer, and my co-worker Jorgen Poff, Volker Deckert, Sebastian Sluker. I worked with them when I was in Germany, and Professor VPS Thana, my PhD advisor, and these are my co-workers. So these are the list of my PhD students. Some few, only two are working, all other have finished their PhD, only last two are working, all other have finished their PhD. Actually, in BHU, we are more involved in teaching, and we find some time and then we work for the PhD students for research. Now I have one information to give to you. Oh, where is, okay. But it is not possible to read it here, so I come back, I tell and then I come back. We are, BHU is also organizing 11th ICO-PVS, International Conference on Perspective of Raman Spectroscopy. I am also convener of that, and I request all of you to look to come attend this conference, and I hope I will get one print and put it here. Anyway, the website is icopvs2026@bhu.ac.in, and also the icopvs https icopvs2026.bhu.edu.in. I request all of you to go on this website and find whether it is interesting for you, and I apply for it. Thank you very much.
So, if there is questions, only one or two questions because lunch time is already coming. Yeah.
Okay. So RK Singhs, I know you, I think 10, 15 years from BSU, I know you.
Yeah. It's my pleasure, sir.
Very happy that you have done very scattering. I want to ask, many people say that Raman scattering is much weaker than excitation intensity, right?
Yeah?
Raman scattering. Raman scattering is much less than of the excitation intensity, right?
Yeah.
Suppose 600 nanometer you do a laser excitation, Raman scattering is very weak, right?
Yeah.
So is that possible too? That Raman scattering is intensity more than of the excitation intensity? Is it possible?
when both intensity,
I
Raman
want
scattering.
opposite. I want opposite. That suppose Raman scattering is more than of the excitation intensity. Is there any opposite emission?
Oh, then we have to go for in case of non-linear Raman spectroscopy.
No, I'm not saying non-linear.
In linear, it is not possible.
No, just
That
linear.
Rayleigh scattering, the intensity of Rayleigh scattering will be always more than the any of the Raman scattering.
Suppose I want to tell you, right? Recently, I published one paper in the, Physics Economic Notice, Journal
Yeah.
Journal of Physics.
Yeah.
This year published it. If you say many people do not think about it, suppose I take 600 nanometer as a excitation source.
Mhm.
But if you do the second overton, or first overton around 300 nanometer, or you take the excitation 300, you take the second order and at 600.
Oh,
you
then
see,
it is
in
non-linear
the time,
effect, na?
When at that time, what one is, I want to tell you, your excitation intensity is weaker than Raman scattering.
Oh, then two photons are used. Though when two photons are being used, then it is non-linear effect.
No, this is not for this. Suppose, so like half of the excitation intensity, you take overton.
Okay.
And all two, suppose 300 excitation I do.
Okay.
Then you take the second order and 600. In that time, Raman scattering intensity is more
Yes,
than
okay,
of your
okay,
excitation
okay.
intensity. Please check, this
Or-
also happen.
Okay, this can be tried because the everyday science has to grow. Otherwise, like Rayleigh scattering, if we can turn Rayleigh scattering, and then again we use it, then also
So
it
this,
can be
please see
possible.
this also, Raman scattering I tell you.
Yeah.
This is very, very interesting. I saw
Yeah,
that.
yeah.
If you do the second order of first overton, is Raman scattering is again more stronger than excitation intensity. If we want, we have
Second order.
Second order or first overton, is intensity is much higher than.
How do you want to get second order without non-linearity?
I tell you, suppose you excite 300 excitation.
Yeah.
You take your, again, up to scanning from, suppose you start scanning from 200 to up to 1000. You excitation. You can get your Raman scattering, both sides 300 and 600. 600
Okay.
means second order I go. If you do 600, you take Raman scattering from 200, you start from 200 nanometer to up to, again,
Okay, sir.
you can get a fast overton,
Yeah.
you can get a.
We will discuss it
So this is very
during
interesting. I want to- this
during
also
lunch
I want to
also.
bring to you, okay?
because from my understanding, some non-linear effect has to be there, but we will discuss it.
Hello, Professor.
Have you met ever? Have you met ever? कभी हम लोग मिले हैं?
नहीं, no sir.
Okay, then because you told you are from NIT. Agartala. I have been there. Okay,
When,
that's
sir?
why I was confused. Okay,
Sir, when you
okay.
were-
Now come to the question. Yeah.
You are in NIT Agartala previously.
Hmm?
NIT Agartala, you are there?
Yeah, I have been.
Okay. So anyway, I was
Yeah,
joined
yeah.
late.
Hope maybe you were not there that time. Yeah. Question.
Professor, that's one slide you have shown that where the antacid need to be given for the bioavailability of particular drugs, lomanamide, I hope so. So thing is that are you expecting the reaction or conversion is going to happen in the stomach or it is happening in the GI tract?
Okay, that part actually what we did, we created a basic medium and reaction started. And even if we put it in water, so reaction, matlab conversion started. This leflunomide converted into teriflunomide. Not only leflunomide, if you take aspirin, then it also immediately starts changing into different drug. Aspirin also, many drugs. So I guess that once we take it orally, it comes in contact with the saliva. That is also water. So it starts breaking. It is converting into teriflunomide from the mouth itself. Everywhere where it gets water.
Okay, that means that simulated media you have prepared and that simulated solution you have prepared and that pH...
in laboratory what we did, we created a basic media. We used NaOH solution or pH of pH 10 and then reaction started. Leflunomide started converting into teriflunomide, but it was very slow. It took hours, 2-3 hours. And in 2-3 hours, we recorded the reminiscence.
As there is no more question, let us thank the Professor Ranjan Kumar Singh for a nice plenary talk.
Thank you, sir, for your wonderful talk. Sir, your kind presence is highly appreciated by all of us, and we would like to present a small gift to express our gratitude. Yeah. I also like to thank our session chair, Professor Saugaijam Dorendrajit Singh, for chairing the session. And we would now like to present a small gift to express our gratitude. May I have the privilege of inviting Professor T.S. Gomti Devi to kindly felicitate our respected session chair. With this, we conclude the current technical session. Lunch will be served at the Department of Physics. We invite everyone to kindly proceed to the Department of Physics for lunch. And after lunch, the third technical session will start, running in parallel in 3 different halls. So please enjoy your lunch. Thank you.